Hi everyone, welcome to my best ever all-in-one Edexcel IGCSE video. I am so excited to share this with you. I'm going to take you through in just the right amount of detail you'll need for your exam, as well as showing you past paper questions to help you perfect your exam technique to make your dream grade a totally achievable goal. I hope you see by the time you've sat through this 4 hours that this has been time extremely well spent. I'm super proud of this video and I hope you enjoy it. Just to introduce myself, my name's Hazel, I'm Science with Hazel. I studied at St John's College, the University of Cambridge. I'm a qualified secondary science teacher and I've been working as a private tutor for over 10 years, so I think I'm well placed to make this content. Throughout you'll see snippets of my revision guide. If you'd like to get hold of a copy, that's available on my website, SWH Learning. There's information there about private tuition if you want help from me or any of our tutors, as well as if you want to sign up to our online revision courses which are held on Zoom that will give you the exam preparation you need to fully ace your exams. But let's just get going. So the thing about physics is I would love to do most of the content talking to the camera, and when there are topics like magnetism and waves, I will absolutely talk to camera. However, when there's lots of calculations, clearly my iPad will be very necessary so I can show you how to work through those types of questions. So I'm really sorry, but the first topic, which is all to do with motion, will be a heavily iPad-based topic. I want to take you through some key motion equations. The first thing I want to make you aware of is the standard scientific unit for these quantities. You will have to do some converting in your exam, so it's worth knowing what the standard units are. Time tends to be in seconds. Acceleration is in meters per second squared. Speed is meters per second. Distance is meters. I'm going to show you a formula triangle now, which has D, S and T in it. D stands for distance, T is time, S is speed. Remember, with formula triangles, they're just really clever ways of helping you remember the correct arrangement of formulae. You cover the quantity you're after. So if I'm after distance, I can see that it is speed times time. If I'm after speed, I can see it's distance divided by time. And if I'm after time, I can see it's distance divided by speed. Next up, acceleration is change in speed over time. To make that more tangible, it's easier to write that acceleration is actually, what is the change in speed? Well, it's the final speed minus the initial speed divided by time, and we can write that as A equals V minus U over T. So V is our final speed, U is our initial speed, T is time, A is acceleration. I want to highlight a special type of equation which we call a SUVAT equation. V squared equals U squared plus 2AS. What does everything stand for? Well, V, as I just mentioned, stands for final speed. U is initial speed. A stands for acceleration. Be careful, S, it stands for distance. That always throws people off. So people do struggle to recognize in the exam that this is the equation they need to use. I'm going to show you an example and then we'll look at a past paper question a little later on. So here a train accelerates from 20 meters per second at 4 meters per second squared over a distance of 25.5 meters. What is the final velocity? My biggest tip here is to just label all your numbers with what they actually mean. So we know that the initial speed is 20, so that's U. Our acceleration is 4 meters per second squared. Here's our distance, and we're being asked to find the final velocity. Write your equation out nice and neatly. Line up all your equal signs. Substitute in your values. We're after V squared. What is our initial speed? Well, we're told it's 20. Our acceleration is 4. And our distance is 25.5. Put that into your calculator and you'll get 604, and then square root to find V. To two significant figures, the answer is 25 meters per second. So let's look at a distance time graph. Distance on the y-axis, time on the x. Remember that speed equals distance over time. So to describe the graph here, at the straight portion of the graph line, we would say that the object is travelling at a constant speed away from the starting point. As the graph line curves, the object must be accelerating. It's steeper here, so we've got faster acceleration up here, and then as the graph line becomes shallower, we have deceleration. At any point where you've got a horizontal line on a distance time graph, clearly the object hasn't travelled any further distance, which is why we would say that the object is stationary. Here we can see acceleration again, the object is stationary. And then this line coming down here, because it's straight, we would say it's a constant speed, but we're going back to the starting point. A lift elevator starts from rest at the ground floor of a building. Figure 1.2 is the speed time graph for the motion of the lift to the top floor of the building. Use the graph to determine the distance from the ground floor to the top of the building. So I want to use this question to show you how to calculate distance from a speed time graph. Now the way you do that is by finding the area under the graph line. It's a very specific thing you have to do. If you're asked to find the distance travelled on a speed time graph, you need to calculate the area of the graph. It's up to you. You could either do this as a trapezium shape, or you could break it up into two triangles and a rectangle, completely up to you. I'm going to go in with the triangle approach. Formula's slightly easier. So I'm going to call that area A, B and C. So when we find the area of this triangle, what is this length here? You can see, according to the scale, it's 7.5. Then look carefully along here, we reach 3.3. And then because it's a triangle, remember we need to multiply that by a half, because that's the formula for calculating the area of a triangle. So that gives me an area of 12.375. What about the area of B? That's slightly more straightforward. We can see that it is 12.5 multiplied by 3.3 again. And now area C, so we've got a triangle again, so we need to multiply by a half. So half times 5 times 3.3. So to find the total distance, we do area A plus B plus C to two significant figures. The distance travelled is therefore 62 metres. I've just cleared my graph again because I want to point out several features that I want you to be able to recognise on a speed time graph. At this portion of the graph, the lift in this case is accelerating. Why is it accelerating? Because remember, our equation for acceleration is change in speed over time. Always bear in mind what the axis labels are, what formula they fit into. What's going on here, if we were to describe this portion of the graph, well, we can clearly see that the lift is travelling at a constant speed of 3.3 metres per second. And then here we would say that the lift is decelerating. It is slowing down because it has a negative gradient. So to reiterate, the area under a speed time graph tells you the distance. If you have a positive gradient, you've got acceleration. A negative gradient on a speed time graph represents deceleration, and then you've got a constant speed here. How do we find the average speed of an object? With physics, it's always useful to state an appropriate equation. Remember that speed equals distance over time. So you need to measure the distance using something sensible like a meter ruler or a trundle wheel. Then you want to time how long it takes for the object to pass between the two distances, taking into account that inaccuracies may be brought about through someone's reaction time. You could improve the accuracy by using light gates. Substitute your values into the equation speed equals distance over time. Remember to repeat for reliability purposes. A car accelerates with a constant driving force along a horizontal road and reaches its maximum speed. This is the velocity time graph for the car's journey. By drawing a tangent to the curve, determine the acceleration of the car at a time of 20 seconds. They very clearly told us to draw a tangent. So they're asking us to look at this point here. Because we've got a curved line though, as they've said, we need to draw a tangent. So that's a line which just touches the point in question. And then we need to find its gradient to find the acceleration, because after all, acceleration is change in velocity over time. So the gradient of my tangent is, count this really carefully, it's 42, my change in y, That's around 5. My change in x is 35, which equals 1.2, which is totally in the acceptable range for this question. Look, 4 marks. Determine the distance travelled by the car during the first 80 seconds of its journey. 5 marks. So to find the distance, remember we need to find the area under the line. This is so nasty because it's a curve. So I'm going to try and estimate as closely as I can. I'm going to take this as being a rectangle though, so I can see that the area of this rectangle is 60 multiplied by 40, which gives me 2,400 meters. Let's make an estimate here. It's kind of just over 1 large square, so I'm going to do 20 times 20, which is 400 meters. Then over here, I'm going to call that 2 large squares, so that will be 40 multiplied by 20, which is 800 meters. And then I'm going to account for this bit here. It's kind of like half a square, so that's 10 multiplied by 20, which is 200 meters. So let's total these up. That gives me 3,800 meters, which is in the acceptable range to get all 5 marks. Explain the motion of the car after 80 seconds. So we're looking at this portion of the graph, we can see it's travelling at constant velocity. And based on the fact that it's travelling at constant velocity, we can infer that the driving force of the car must be the same as the air resistance, which, remember, is acting in the opposite direction, meaning that the resultant force is 0. So the car travels at constant speed, and we need to explain why. Air resistance equals driving force. A bus travels at a constant speed. It stops for a short time and then travels at a higher constant speed. Using the axis in figure 1.1, draw a distance time graph for this bus journey. So think very carefully about the various portions. So initially it's travelling at a constant speed. Remember, speed equals distance over time. So what we need is a positive gradient, and because it's constant, we need that line to be straight. They're not going to be particularly fussy about what gradient you use. It says it stops for a short time. That means that it's stationary and goes no further distance. So in terms of our graph line, we need to draw a horizontal portion to represent the fact that it hasn't moved any distance whatsoever. And then it says that it travels at a higher constant speed. So again, we need a straight line, but because it's traveling at a faster speed, we need a steeper gradient. So something like that. The graph shows how the thinking distance and braking distance of a car vary with its initial speed. A car has an initial speed of 35 meters per second. The brakes are applied and the car comes to a complete stop in the braking distance shown by the graph. Calculate the mean braking acceleration of the car. So we've been given you the initial speed. I can infer the final speed because we know that the car's coming to a complete stop, which means its final speed must be 0. We need to find the acceleration. The only thing I'm missing in order to use this SUVAT equation is the distance travelled, but we can work that out using the graph. So I'm going to go up at 35 meters per second. I know that I need to look at the braking distance line because I've been told there. Read that really carefully across. 78 is your distance. This is why this question is worth 4 marks. So substitute in V as being 0. U we know is 35. We're after the acceleration and we know the distance is 78. Sort out the right hand side. So I'm simplifying the whole way. How do we get A by itself? First of all, we need to minus 1,225 from both sides. And then our final step is to divide both sides by 156. So to 2 significant figures, my answer is minus 7.9 meters per second squared. Let's discuss the different types of forces. You do need to provide these as a list. They are gravitational force, electrostatic force, weight, normal reaction, friction, air resistance, upthrust, nuclear and magnetic, just to provide a little more detail on some of those. So remember, the gravitational force is what causes objects, once dropped, to move towards the Earth. Friction occurs between an object and the Earth's surface. A good place for friction is a car's tyre. Air resistance is all about opposing motion. So if a parachutist jumps out of a plane and their weight is acting downwards, you'll find that the air molecules collide with the parachutist as they fall towards the earth, and that's what we call air resistance or drag, because it will act to slow down that person. The normal reaction occurs anywhere where you've got an object touching a surface. It's a force which acts at 90 degrees. So just to distinguish now between scalar and vector quantities, the main difference, if you're asked to define them, is that scalar has a magnitude only, a size, such as 10 meters per second for speed, whereas a vector quantity has both a direction and a magnitude. So if we take velocity, how we can differentiate that from speed is, yes, it can have a size like 10 meters per second, but it will also have a direction, such as the car moves 10 meters per second in a northerly direction. They quite like asking you to name scalar and vector quantities. The easiest thing to remember is that there's actually only 6 vector quantities. They are displacement, acceleration, weight, velocity, force, and momentum. Everything else is a scalar quantity. We mentioned various forces. Let's have a look at a detailed force diagram here. I'm just using a car as a simple example. So you've got the weight of the car acting downwards. As I said, friction will act at its tyres to oppose the motion that occurs between the tyre and the road. The normal reaction is at 90 degrees to where the car's tyres touch the road surface, and then you'll have a driving force being produced by the engine. Sometimes they allow you to calculate a resultant force. All that means is looking at the forces acting in opposing directions. So for example, if this car has a driving force of 100 newtons, friction is 80 newtons, then the resultant force would be 20 newtons. Let's go through Newton's laws. So Newton's first law states that if forces acting on an object are balanced, the resultant force is 0. So if the object is moving, then it will continue to move in the same direction at the same speed, as long as the resultant force is 0. If the object is stationary, it will remain at rest. Newton's second law is really an equation which states that force equals mass times acceleration. What that means is acceleration is directly proportional to the resultant force, and it's inversely proportional to the mass of an object. When thinking about vehicles' motion, we like to talk about stopping distance, braking distance, thinking distance. So a stopping distance is the distance that the car travels from the moment that a hazard is spotted until that car comes to a rest. It consists of 2 quantities, both the thinking distance and the braking distance. So the thinking distance is the distance travelled by the car from the moment the person spots the hazard until they apply their brakes. The thinking distance can be affected by distractions like loud noise, loud music, being under the influence of drugs, including alcohol, how fast your reaction time is, and if you're tired. Now, the braking distance is the distance travelled from the moment the car's brakes are applied until the car comes to a stop. Lots of factors affect braking distance, including the condition of the road. So if it's icy or wet, that will reduce friction. The condition of the car's tyres, again, if they're worn, that will reduce friction. The condition of the car's brakes. How many people are actually in the car? So the mass of the car, the heavier it is, the further it will travel during braking. And the speed of the car will also have a huge effect. Let's have a look at terminal velocity now. So what happens to a parachutist when they jump out of a plane? Let's think about the various forces which act on the person. So initially, the parachutist starts falling towards the Earth's surface, and that's because the weight is acting downwards, and they will accelerate towards the Earth's surface. Because you've got more air molecules hitting that parachutist per second, you will find that the air resistance increases as the parachutist accelerates. Eventually, you reach a point where weight equals air resistance. Because the forces are balanced, we would say that there's no resultant force and that the parachutist travels at a constant speed. Terminal velocity has been reached. What happens next if the parachutist opens their parachute is due to that huge increase in surface area, you've got far more air molecules colliding, meaning the air resistance massively increases. Air resistance is greater than weight, so the person slows down. And then as they slow down, the air resistance will decrease and eventually their weight will equal air resistance. So we have no resultant force and the person travels at a constant velocity, a new terminal velocity, but this will be lower than the original terminal velocity. Let's also consider terminal velocity from a velocity time graph perspective. By the way, this is taken from my revision guide, which is available on the website. So if we actually have a look here, you can see due to that steeper gradient that the skydiver is accelerating. And as I've said previously, that's because the weight force is greater than air resistance. Because that skydiver or parachutist speed is increasing, we know that air resistance will increase, and as a result, acceleration decreases as seen by the shallower gradient here. Eventually, weight equals air resistance. We say that there's no resultant force, the forces are balanced, and a constant velocity, a terminal velocity is reached. And as we would expect on a velocity time graph, a constant velocity looks like a straight horizontal line. Then the parachute is opened. As a result, air resistance massively increases, so the person decelerates further. They slow down, as seen by this negative gradient here. And then eventually we know that we're going to reach a new terminal velocity where weight equals air resistance. There's no resultant force. A new constant speed is reached, and as you'd expect, again we see a horizontal portion of the graph. Diagram 1 shows a van accelerating along a horizontal road. The horizontal forces acting on the van are shown. So we've got a driving force of 2,500 newtons and an opposing force, force X. Force X opposes the motion, state the name. That's either drag, air resistance. I would pick either of those two because the arrow's not acting here where the wheels touch the road, but they'd have also allowed friction. The resultant force acting on the van is this. Calculate the magnitude of force X. Assume X is the only horizontal force opposing the motion of the van. We have a driving force acting in this direction. We have force X acting in the opposing direction, and the resultant force is 1,500. So actually, your resultant force equals your driving force minus force X. So you just need to solve that equation. To get 1,000 newtons. Diagram 2 shows the resultant force acting on the van when it brakes. State the formula linking resultant force, mass, and acceleration. Force equals mass times acceleration. The mass of the van is 1900 kg. Calculate the acceleration of the van when it brakes. Give the unit. It's up to you if you want to rearrange the equation or just put the numbers in as they are. You'll see me doing both throughout. So the mass of the van is 1900. The resultant force is 14 kN. We need that in the standard unit of a newton, so we need to multiply that by 1,000. They will try to constantly catch you out with units. We're after acceleration, so we do 14,000 divided by 1900 to get 7.4. Technically speaking, it's braking, so it will be slowing down, so it'll have a negative acceleration, but they won't knock a mark off if you don't include the minus. The units of acceleration are meters per second squared. The van was travelling at an initial speed of 18 meters per second before braking and coming to rest. Calculate the distance travelled by the van while it is braking. Assume that the acceleration remains constant. Let's label everything we have. We have a final speed, v, an initial speed, u. We're after distance, which is s. We know a. So actually we need to use SUVAT, which is v squared equals u squared plus 2as. Sub in your values. Sort out the right hand side. So to two significant figures, that's 22. So including the minus sign here for my acceleration obviously became very important with my final answer here. Describe two factors that would increase the braking distance. Let's talk about the condition of the tyres. So worn tyres, meaning that there'd be reduced friction. Increased mass of van. When the van is fully loaded, its mass increases to 2,500 kg. Calculate the time taken to bring the fully loaded van to rest when it is travelling at an initial speed of 18 meters per second. Assume that the resultant force remains at 14 kN. So this is worth 4 marks, so try and use the fact it's worth so many marks to indicate that you might need to use more than one equation. I've labelled everything to help clarify which equations I need. So I know that I'm going to need to find t. I've got a v and a u, which means that acceleration is final speed minus initial speed divided by time is probably going to be useful. However, I don't have a yet, and therefore I don't have enough information to use this equation. But I have a mass and a force, which means I can use this equation, force equals mass times acceleration, to find my A value, which I'll then sub into this equation. So let's pop in our numbers. Solve for A. The acceleration is 5.6. I'm going to pop it into the equation over here. What was my final speed? Well, we were told the van was at rest at the end, so that will be 0. The initial speed was 18, and I'm after t. Cross multiply to get 18 divided by 5.6. Our final answer is 3.2 seconds. The graph shows how the velocity of a parachute jumper changes with time. At point 8, the parachute jumper is falling at terminal velocity and has not yet opened her parachute. So we know there that the forces are balanced. There's no further acceleration because she's falling at terminal velocity. So which statement is correct about the parachute jumper at point A? Acceleration and air resistance are equal. No, that's not true. Acceleration and velocity are equal. No, that's not true. Weight and acceleration are equal. No. Weight and air resistance are equal. Yes, because those are forces acting in opposite directions. So that is what's responsible for there being no resultant force and terminal velocity having been reached. Which is the best estimate of the distance fallen by the parachute jumper from the start until point A? So we are looking only at the area under the graph, but for this portion of the graph from the start to point A. So they want us to estimate. I'm going to estimate that as a square. So I'm finding the area of 54 times by 50. But obviously I need that number to be slightly less because it's not a full square. But let's see what we have here. Oh yeah, perfect. Which is the best estimate? Look, I need it to be slightly less than that, so I'm going to go in at C, 2,300. The parachute jumper opens her parachute at point B. Her velocity decreases. That's because we've got a huge amount of air resistance produced by the parachute being opened. So her velocity decreases until she reaches terminal velocity again at point C. Explain this change in velocity. So there's point C. So yeah, as I was saying, as she opens the parachute, what happens is the air resistance massively increases due to that larger surface area provided by the parachute. And as a result, her air resistance will be greater than the weight. Therefore, there'll be an upwards resultant force, meaning that her speed slows down. In effect, she decelerates. And then because she's going slower, there will be fewer air molecules colliding with her per second, meaning the air resistance will decrease. So eventually you'll get a new situation where a new terminal velocity is achieved and her resultant force becomes 0 again due to air resistance equaling weight again. You really do need to understand terminal velocity to be able to answer these questions. So when the parachute opens, air resistance increases hugely. Air resistance is at this point is greater than weight. So she starts to decelerate. As she slows, air resistance decreases because I said fewer air molecules will be colliding with her. And eventually, air resistance equals weight and the forces are balanced. There is no resultant force, so a new constant speed is achieved. So Hooke's law is just a small off-branch of the forces topic. So with Hooke's law, what you're doing is you're investigating how the length of a spring changes when you add different weights to it. In terms of planning an investigation, first of all, you need to measure the length of the spring unextended, so its original length, and then you need to add weights incrementally. So for example, add a 10 Newton weight, measure the new length of spring, add a 20 Newton weight, measure the new length of the spring, 30 newtons, and so on and so forth. Now, in order to find the spring extension, you need to take away the original length of the spring away from the final length of the spring. You'll then be ready to plot a graph On the y-axis, you want to plot extension in centimetres or metres, and then on the x-axis, you'll want to include either load or weight that's measured in newtons. Now, to begin with, you'll probably find that your relationship is directly proportional. We can see that because the graph line is straight and it passes through the origin, so 0, 0. However, as you add more weights, what's going to happen is your spring will deform. We say that its elastic limit has been reached, its limit of proportionality has been reached, and the spring is permanently deformed, so you'll see that the graph line in effect starts wiggling, and it is no longer a directly proportional relationship between load and extension. In terms of the definition of elastic behaviour, this is the ability of a material to revert to its original shape after forces causing deformation have been removed. If you're asked to state Hooke's law, you want to say that the extension of a spring is directly proportional to the force applied, provided its limit of proportionality has not been exceeded. A student investigates how the extension of a spring varies when the mass attached to the spring is changed. The diagram shows most of the equipment the student uses in the investigation. Describe a method the student could use. Your description should include the measurements taken and how the student could obtain accurate results. Although the variable layout doesn't work quite as beautifully in physics compared with chemistry and biology, I'm still going to use it here, but we do need to provide some extra method points. So my independent variable, what am I changing? Well, it says here that we're changing the mass attached. Use a variety of masses, e.g. 10 grams. Okay, the dependent variable is very important because they've actually mentioned, what are we measuring here? So the first thing we need to do is measure the original length of the spring. It's always worth mentioning apparatus. Using a ruler. Add the mass, measure the new length of spring. Spring extension is therefore new length minus original length. I'm not going to include any control variables here. I'm just going to simply say repeat and calculate an average for reliability. And then the other thing I want to point out is this whole thing about getting accurate results is all about how we use the equipment and what equipment we choose to use. So you want to read ruler at eye level to prevent parallax issues. And I've definitely got 5 marks worth of points there. The student calculates the force each mass applies to the spring. The table shows the student's results. Plot the student's results and draw a circle around the anomalous point. I'm just going to move it so I can see it. So I'm plotting force along my x-axis. Don't forget your units. Extension is on my y-axis. Pick a sensible scale, occupying as much of the graph paper as possible. Our extension goes from 0 to 20. Plot with nice, neat crosses. They need to be crosses rather than dots. You can see this is our anomalous result. Now we'll draw in a line of best fit. Explain whether the spring obeys Hooke's law. So we need to make a comment. Does it obey? Yes. The force and extension are directly proportional. They pass through 0, which is the origin. And we have no deformation of the spring up here. There's no wriggling line, which means that the spring hasn't reached its elastic limit. Momentum now. This is a largely calculation-based topic. First of all, I need you to remember that it is what's known as a vector quantity, and that means it has both a direction and magnitude. The equation for momentum looks like this. Momentum equals mass times velocity. In terms of working out the units of momentum, just sub in your units of mass, kg, your units of velocity, meters per second, so you can see that the unit of momentum is kilograms meters per second. One thing it's worth learning is the law of conservation, which states that in a closed system, the total momentum before an event is equal to the total momentum after the event, and we'll use that a lot in the more complicated calculations. So let's work our way through some calculation examples, and then I'll do some past paper practice. We'll start nice and straightforward here with question 2a. Calculate the momentum of an 80 kilogram rugby player running at a velocity of 5 meters per second. Get used to writing your equations. So we do our mass, which is 80 kg, our velocity is 5, to get an answer which is 400 kilograms meters per second. An 800 kg car moves at the same momentum as the rugby player in part A. Calculate the velocity of the car. So write our equation again. Momentum equals mass times velocity. We've been told that the momentum was the same. The mass was 800. They want us to find the velocity, so we do 400 divided by 800 to get 0.5 meters per second. A 1,000 kilogram rail wagon moving at a velocity of 5 meters per second on a level track collides with a stationary 1,500 kg wagon. The two wagons move together after the collision. Calculate the momentum of the 1,000 kg wagon before the collision. So momentum equals mass times velocity. Its mass was 1,000 kilograms. Its velocity was 5. So our final answer here is 5,000 kg meters per second. Now this is a really common type of question, this thing where two objects move together, collide, potentially stick together. So I'm going to show you the easiest way of answering the next bit of the question, which is that you need to state the conservation of momentum, which remember is that momentum before equals momentum after. So you need to work out the momentum of the two wagons before the collision and then their momentum afterwards. So the momentum before, well, we just found out what the momentum of the 1,000 kilogram rail wagon was. It was 5,000. What about the momentum of this wagon? Well, we're told it's stationary, so by definition, its momentum must be 0 because after all, its velocity will be 0. What about the momentum afterwards? Well, we know that they join together after the collision, which means that in order to find the mass, we need to combine both masses to get 2,500, and then their velocity will be a joint velocity, so we're going to call that v because that's what we're after. So now it's nice and straightforward. We've got 5,000 equals 2,500 v. To solve for v, we divide both sides by 2,500 and we get an answer of 2 meters per second, which happily is exactly what we're after because they say in part B, show that the wagons move at a velocity of 2 meters per second after the collision. So this is a very typical momentum calculation, and it is saved from being too difficult if you write the statement that the momentum before equals the momentum afterwards. Another type of question you could be asked about is a recoil velocity question. I'll take you through this example and you'll see that it's actually really similar despite the fact that this time you're firing a shell. So an artillery gun of mass 2,500 kilograms fires a shell of mass 25 kilograms at a velocity of 140 meters per second. Calculate the recoil velocity of the gun. So again, we're going to write our conservation of momentum statement, which is momentum before equals momentum after. So what is the momentum before? Well, before, nothing has happened, right? We haven't fired our gun yet. So by definition, in these type of questions, the momentum before must be 0. Let's work out the momentum after the gun has been fired. So we need to do the mass of the gun, which was 2,500, multiplied by its velocity, which we've been asked to find. And then we need to add it to the momentum of the shell. Its mass was 25. We were told its velocity is 140. Now we need to solve for v. To get v by itself, we first of all need to take away 3,500 from both sides. and then divide by 2,500. It makes sense that the answer is minus because the shell and the gun are moving in opposite directions. I want to show you one final type of momentum calculation whereby force equals change in momentum over time. This is another really important equation. And so if we were to really break up what we mean by the change in momentum, we can see that it is mass times the final velocity minus the mass times the initial velocity. Because remember, momentum is calculated by doing mass times velocity. So in this example here, in a crash test, a car runs into a wall and stops. The momentum of the car before the crash is 22,500 kg meters per second. The car stops in 0.14 seconds. Calculate the average force on the car during the crash. So after force, what is our change in momentum? Well, the momentum before, we were told, is 22,500. The momentum after, by definition, must be 0 because it says that the car stops. So what must the change in momentum be? Just 22,500. And the time, we're fine with our units, it's in seconds. So we divide by 0.14 to get 160,000 Newton force to 2 sig fig. One thing I just want to quickly mention, they love asking you things like, why does the seatbelt help keep people safe in cars? How does a crumple zone on a car work? An airbag? The answer is always this. You want to state the equation, force equals change in momentum over time. Regardless of the fact that you have seatbelts, crumple zones, airbags, etc., you're going to still get the same change in momentum. However, by including these sorts of safety devices, what you're actually doing is increasing the time of impact. So this number remains the same, but it's divided by a larger number, which obviously means that your force calculated will be less. So it reduces the force felt by the person, meaning that the person's less likely to suffer from serious injury. The diagram shows the collision between two balls A and B. The masses and velocities of both balls are shown before and after the collision. Ball B is stationary before the collision. When the balls collide, ball B applies a force on ball A, which causes the velocity of ball A to change. Ball A also applies a force on ball B during the collision. Describe how the force applied on ball A compares with the force applied on ball B during the collision. Now this is really checking that you're aware of Newton's third law, which states that every force has an equal and opposite reaction. So I'm going to say here that both forces are the same size, but the forces are acting in opposite directions. If you'd stated Newton's third law, you would have also got a mark. Calculate the momentum of ball A before the collision. So momentum equals mass times velocity. We're being asked before the collision. So we're looking at this. Luckily, everything's in the right unit. Our answer here is 0.088. Show that the velocity v of ball B after the collision is about 0.6 meters per second. So we need to write here momentum before equals momentum after. The momentum of ball A before the collision we've just calculated is 0.088. The momentum of ball B before the collision, we were told it was stationary, so by definition it's 0. What about the momentum of each of the balls afterwards? Just check the directions. Look, ball A is moving in the opposite direction to what it was doing before, so when you work out its momentum, we need to do minus 3.5 for its velocity multiplied by the mass. So minus 3.5 multiplied by 0.018. What about the momentum of ball B? We've got its mass here, 0.265, and we're after its final velocity. So really take your time laying out your answer properly. Will make things so much more straightforward for you. Sort this out here. We need to get this by itself, so we need to add 0.063 to both sides. Lay your answers out nice and neatly so the examiner can really see what you're doing. To find V, divide both sides by 0.265. So we can see that the answer is correct because look, it's approximately 0.6. Another calculations heavy topic is moments. The word moment refers to the turning effect of a force. In everyday life, you'll see moments in action when you're using a spanner or a wrench, when you're using a seesaw at the park, and even when you're opening a door. Now, the equation for moments is moment equals force times perpendicular distance from pivot. Remember, perpendicular means at right angles. In terms of the units, force, remember, is newtons. Our standard scientific unit for distance is meters, so our standard moment unit is Newton meters. Occasionally you'll see it in centimeters, but you do need to check the wording of the question. Be prepared to state the principle of moments. The principle of moments states that at equilibrium, the sum of the clockwise moments equals the sum of the anti-clockwise moments. And we'll use that statement time and time again when we do calculations. One extra thing to point out is how do we increase the size of the turning effect, the moment? Obviously, if we increase the force applied and or the perpendicular distance from the pivot, you'll increase the size of the moment, which is why wrenches or spanners with longer handles are better at undoing bolts. But I think the best thing to do is look at some questions, really as many as possible. The diagram shows how a mechanic applies a force on a spanner to try and undo a bolt. State the equation linking moment, force and perpendicular distance from pivot. We just did this. Calculate the force required to produce a moment of 4.8 Newton meters. I'm just going to reduce perpendicular distance from pivot to distance so I can fit it in better. So we're trying to produce a moment of 4.8. We're being asked to calculate the force. What is the perpendicular distance from the pivot? This question is a little bit confusing. We've got 3 distances to pick between, but look, the force is being applied in this direction. So if we take the perpendicular distance, it has to be the one at right angles, which is 40 centimeters. Just be careful with units. We need that in meters. To solve for x, you need to divide both sides by 0.4. The answer here is 12 newtons. The mechanic is not able to undo the bolt because a moment of 9.6 Newton meters is needed. Explain how the mechanic could produce a moment of 9.6 Newton meters. Just have a look. Look, that number is double the original moment. So how do we make this number here double? Well, either we double the force or we double the distance from the pivot. Another question now. The man exerts a total upward force of F newtons. The weight of the loaded wheelbarrow is 470 newtons. Mark X on the diagram to indicate the centre of gravity. That will be here. State the equation linking moment, force and perpendicular distance from pivot. Calculate the force F. So this is one of those situations where you want to state the principle of moments. So you want to say that clockwise moments equals anti-clockwise moments. So what is our clockwise moment? If this is the pivot, then the clockwise moment will be acting in this direction here, following the clock face. This force being applied in this direction will form part of the anti-clockwise moment. It does take a little bit of practice, but what is the clockwise moment? As I said, it's going in this direction. So to find that moment, we do force times perpendicular distance from pivot. Do not be tempted to work out that answer and write it here. No, you need to find the anti-clockwise moment. Well, we need the force, so that's what we're trying to find out, F, times the perpendicular distance from pivot. Here's the pivot. Make sure you add these two numbers together to find the correct perpendicular distance. That's 1.4. Sort out the left-hand side, so 470 times 0.6 to get 282 equals 1.4F. And then divide both sides by 1.4 to find F. to 3 significant figures, our answer is 201 newtons. A wrench is used to turn a nut. The force applied to the wrench is 28 newtons. Calculate the moment applied by the wrench on the nut, give a suitable unit. So moment equals force times perpendicular distance from pivot. The force we were told is 28 newtons. Now, in terms of the distance, it's kind of up to you because they're allowing you to choose your own unit. Personally, I'd always go for the standard unit, which in the case of distance is meters. So I'd put that as 0.15. Pop that into your calculator to get 4.2, and then just sub in your units, you can see that that is Newton meters. State 2 changes that could be made to increase the size of the moment applied to the nut. Well, think about what we have going on in this equation. How do we increase that value? We can apply a larger force, or we can increase the distance, i.e. have a longer wrench. Diagram 2 shows the wrench as it is turned through 90 degrees. The force is applied over a distance that is equal to a quarter of the circumference of a circle. The circle has a radius of 15 centimeters. Calculate the distance over which the force is applied. Here's your equation for circumference. This is quite an unusual one. This is just more standard maths. Just make sure you read it really carefully. So it says here the force is applied over a distance which is equal to a quarter of the circumference of the circle. So we need to find a quarter of the circumference of the circle. So circumference is 2 pi r. The radius, we were told, is 15 centimeters. Put that into your calculator and then just divide by 4 because we need it to be a quarter of its value to get 23.6. Calculate the work done by the force as the wrench is turned through a quarter of the circumference of the circle. So work done is force times distance. Get that unit of distance into your standard unit of meters. So we do 23.6 divided by 100 to do that. The reason that I'm doing that is because, look, I need my standard unit of energy there, which is joules. And they told us that the force was 28 newtons. So we get a value of 6.6 joules. Let's look at a really important topic now, which is electricity. It's divided into mains electricity, energy and voltage in circuits, as well as static electricity. We're going to start by looking at electrical circuits, which if you're at school, you might have built some simple circuits using various components. We're going to go through the standard symbol used for each of these components. Then we'll take a deep dive into the differences between current, voltage, charge, resistance, etc. And then we'll look more generally at mains electricity to do with plugs, Ohm's law, etc. We'll also contemplate the difference between series and parallel circuits and the various advantages and disadvantages of both of these types of circuit. When we contemplate electricity, really we're looking at a small subatomic particle known as electron and how it can flow around a circuit. So in order to allow the flow of electrons, we need a metal. Metals, after all, are good conductors of both heat and electricity because they have a sea of delocalized electrons. Now, if we consider the structure of a metal further, there's also a regular arrangement of positive metal ions. These vibrate slightly and get in the way of the flow of electrons, and we call this resistance. If you were to increase the temperature of a metal wire, what happens is that you increase the resistance because the positive metal ions vibrate more and they impede or inhibit the flow of electrons. Plastics are electrical insulators because they have no free electrons, and here's the symbol which refers to something which has double insulation, which effectively means it has 2 layers of plastic, which means it's incapable of becoming charged and causing an electric shock. So going back to resistance, now resistance is measured in ohms, and really it's the opposition to the flow of charge. Going back to our wire, the longer the wire, the greater the resistance, and the larger the cross-sectional area of a wire, the lower the resistance. So to have as low a resistance as possible, ideally you want a short fat wire. What is current? It's the rate of flow of electrons carrying a negative charge, and it's measured in amps. You'll often find in the questions that the question provides milliamps. Most likely you'll need to convert that to the standard amp unit by dividing your number by 1,000. Now you can measure the current of a circuit by adding an ammeter to the circuit. Just be aware that that ammeter needs adding in series, which means it needs to be part of the main circuit. It's very important that you're clear that an ammeter is added in series, whereas a voltmeter, which measures voltage or potential difference, must be added in parallel, which means it must be added as a separate branch around the component that you are interested in. And it makes sense really if you know that voltage is a measure of energy transferred between 2 points of a circuit. One of the equations for calculating voltage states that voltage is energy divided by charge. So if we were to define a volt, consider the units of both energy and charge. The unit of energy is joules, the unit of charge is coulombs, and that will actually help you define what a volt is. 1 volt means that 1 joule of energy is transferred per coulomb of charge. So just to reiterate some key units, we say that current is measured in amps, voltage is measured in volts, charge is measured in coulombs, resistance is measured in ohms, energy or work done is measured in joules, power is measured in watts, and time will always come up in electricity, is measured in seconds. And just to remind you, often you get something like 7 milliamps as being described as being the current. You need to convert that into amps by dividing that value by 1,000. Let's look at some key electrical components. So you need to be able to draw these and form your own circuits. Here is your filament lamp or bulb. You might want to dictate whether there's a current flowing by having a switch. If the switch is open, no current will flow because obviously you've got a break in the circuit. If the switch is closed, then the current can flow. We need to be able to push those electrons around the circuit, and we can use a cell to do that. You'll be more familiar with multiple cells in a line, which we call a battery. This is a fixed resistor. Remember that as resistance increases, current decreases. This is what's known as a variable resistor. This is a thermistor, a temperature-dependent resistor. This is a light-dependent resistor known as an LDR. Here's your fuse, not to be confused with the resistors, which acts as a safety device. It melts when the current's too high, preventing fires. This is a diode, which allows current to flow in one direction only. If there's 2 arrows pointing away from the diode, it means it's a light-emitting diode. Here's your ammeter, which measures current. Remember, we add it in series. Here's your voltmeter, which measures voltage or potential difference. Remember, we add that in parallel. I just want to show you how to measure resistance of a bulb. You can't measure that directly. You don't have a resistor that will do that. But one of the equations you need to familiarize yourself. Here's the formula triangle. Just be a little bit careful. This is voltage. R is resistance. And then confusingly, I stands for current. Really, it stands for intensity of current. But there's the I. So how do we measure the resistance of a bulb? Well, we can see that if we know voltage and we know current, we can divide the voltage by the current in order to find the resistance. And I'm hoping you can see, therefore, that it is a straightforward thing to add a voltmeter to measure the voltage, an ammeter to measure the current. Once we find those two values, we can sub it into this equation in order to calculate the resistance of whatever component you're being asked about. So just to show you, here's our filament bulb. We'll need a way of pushing electrons around the circuit, so I'm going to add a cell. You'll need a way of altering the resistance of the circuit, so I need to include a variable resistor. I need a way of measuring current, so I need to add an ammeter, which remember I said needs adding in series, which is why it's part of the main circuit. And I'll need a way of measuring voltage, so I'll add a voltmeter here. I'm adding it in parallel, which is very important, and I'm making sure it's going around the component that I'm interested in. So to reiterate, to measure the resistance of a bulb, find the voltage using the voltmeter, find the current using the ammeter, and then substitute those values into the equation resistance equals voltage divided by current in order to calculate the resistance. So there are various types of resistor. Fixed resistor, a thermistor, and a variable resistor are all types of resistor you need to familiarise yourself with. Now, a thermistor is a special type of resistor whose resistance depends on temperature. The higher the temperature, the lower the resistance of a thermistor. You could be asked to show the relationship between these two quantities on a graph. Notice that the relationship is non-linear because you don't have a straight line, and it is absolutely not directly proportional. A light-dependent resistor obviously depends on light. The higher the light intensity, the lower the resistance. Again, if you look at the relationship between these two values, it's a non-linear relationship. The fuse is an incredibly important safety device. The role of the fuse is to prevent fires. Due to some kind of abnormality, the current can rise too high. As a result, the wire in the fuse melts, breaking the circuit, meaning that no more current can flow. They often ask you to choose a fuse with a current rating that is appropriate to a particular setting. So for example, say you have a kettle which uses 15 amps. What would be an appropriate fuse to use in the plug of the kettle? Something like 16 or 17 amps, because you definitely don't want to choose a fuse with a current rating which is lower, because obviously that fuse wire will melt every single time the kettle's switched on. But equally, you don't want to pick a fuse with a current rating too high because it won't operate appropriately as a safety device. A diode is used to allow current to flow in one direction only. A special type of diode is a light-emitting diode. As the name suggests, when the current flows through the diode in the correct direction, you will see light. It's a good way of showing that a particular device is working. Let's contemplate some differences between series and parallel circuits. So I'll draw some simple circuits here. Here's a cell, some wires and a bulb. This is a series circuit because everything is part of the main branch. A couple of things to be aware of is that voltage is shared between components in a series circuit, whereas the current is the same everywhere. So what do we really mean by that? Well, let's look at a scenario where I add another filament bulb into my circuit, which has the same resistance. If I have 6 volts coming from my cell, because the voltage is shared between them, each bulb will receive 3 volts. That means that these bulbs will dim. They'll be half as bright as the original bulb. So it's not a great scenario if you want really bright bulbs. It also means that if one of the components fails, the whole circuit goes off because there's a break in the flow of electrons. However, one advantage is that you can use fewer wires and there's less chance of overheating. What about if I were to take a parallel circuit? So really similar. This time the voltage is the same everywhere, whereas the current is shared between the components. So what does that mean? Well, we'll add another bulb in parallel, because after all, parallel means that it'll be on a separate branch. Because the voltage is the same everywhere, both bulbs receive 6 volts. So you will find that those bulbs stay nice and bright. Clearly the battery or the cell will run out faster. One advantage, however, is if one of these components fails, there's another path for the electrons to flow around, so the other bulb will still work. We've looked at this formula triangle, so I won't repeat myself there. Let's look at a couple of extra formulae. So Q equals IT. Q stands for charge, T stands for time, I stands for current. So we can see therefore that charge equals current times time. What about current? Cover what you're after. It's charge divided by time. There's the divide sign. And time, we can see cover T is charge divided by current. What about PIV? Power, voltage, current. Power equals current times voltage. Voltage equals power divided by current. Obviously, it depends what year you're sitting these exams. Some of you have been lucky to have received the formula sheet. Still worth knowing about the rearrangements though. And then a particular favourite, E equals IVT, stands for energy equals current times voltage times time. If you prefer, you can say that energy equals power times time, because after all, power equals current times voltage. Let's look more closely at the structure of a plug. So first of all, you have 3 wires. The green and yellow wire is known as the earth wire. For some reason, thinking that the green looks like grass, the yellow looks like sun, helps me remember that it is the earth wire. The live wire is confusingly brown in colour, and the neutral wire is blue. What is the purpose of the earth wire? Well, particularly in devices which are made out of metal, what happens with the earth wire is it helps excess charge drain to earth, helping prevent electrocution. The cable grip is made out of plastic because you need to use an insulator. The pins of the plug are made out of brass because brass is hard and a good conductor. And obviously inside the plug you'll also find a fuse which acts as a safety device, helping prevent fires. Now, an alternating current is a current which continuously changes direction. You find that we have an alternating current in our main circuit. A direct current is a current which flows in one direction only. You find a direct current in batteries. Let's look at these current voltage graphs now. As you can see with the wire, we have a directly proportional relationship between voltage and current. I know that because I can see a straight line which passes through the origin. This means that the resistance doesn't change and that it obeys Ohm's law. A filament bulb now has a distinctive sigmoidal shape. Clearly this is not a directly proportional relationship, and the reason you get that characteristic shape is that at higher temperatures, which mean higher resistance, you find that the current decreases, and that's responsible for the shape of the curve we see here. With a diode, because it only allows current to flow in one direction only, you get a very distinctive graph line. This is because you get a high resistance when the current flows in one direction and a low resistance when the current flows in the other direction. Underpinning looking at these graphs is Ohm's law, which states that the current through a wire or resistor at constant temperature is directly proportional to the potential difference or voltage across the wire or resistor. The teacher uses this circuit to investigate how the current in a circuit changes with the temperature of a room, calculate the voltage across the thermistor. So just to be aware, look, we have a cell here, here's some wires, here's our thermistor, which is our temperature dependent resistor. We've got a fixed resistor here and a voltmeter measuring the fixed resistor's voltage. Calculate the voltage across the thermistor. So we need to find out the voltage here. Remember, your voltage rules in a series circuit state that the individual voltages of the components add up to the total voltage. So to work that out, we need to do our total voltage equaling the voltage in our thermistor plus the voltage over here of our fixed resistor, solve for X, and you'll get an answer of 0.59. State the formula linking voltage, current, resistance, V equals IR. Calculate the resistance of the thermistor, resistance equals V over I. I just found out the voltage of the thermistor. It's 0.59 volts. What about the current? Well, again, you need to remember your series circuit rules, which state that the current is the same everywhere. So our current is 6.2 milliamps. That needs to be converted into amps by dividing by 1000. You need your standard unit here. And that gives you a final answer of 95 ohms. The graph shows how the resistance of a thermistor changes with temperature. Describe the relationship between temperature and the resistance of the thermistor. So we can see, due to the curved line, that it's a non-linear relationship, but you can also see that as the temperature increases, the resistance of the thermistor decreases. The photograph shows a power bank used to recharge the battery in an electronic device. The power bank stores charge. The charge stored can be measured in amp hours. 1 amp hour is the amount of charge transferred by a current of 1 amp in a time of 1 hour. Calculate the charge stored in coulombs when the charge stored is 1 amp hour. So we're told that the current is 1 amps. We have an hour, we need that in seconds, so we need to multiply it by 60 twice to get 3,600 coulombs. An electronic device is connected to the power bank. Whilst recharging, the electronic device receives a constant current of 2.4 amps and 3.8 times 10 to the 3 coulombs of charge is transferred. Calculate the time taken to recharge the electronic device. Give your answer in minutes. So time equals charge divided by current. Our charge is 3.8 times 10 to the 3. The current is 2.4, which equals 1600 seconds. They want the answer in minutes, so you do need to practice your unit conversions. You need to divide by 60 in order to do that. So our answer is 27 minutes. The electronic device is connected to the power bank using a long cable. Suggest how using a long cable affects the time taken to recharge the electronic device when compared with a short cable. Remember that the length of your wire really affects your resistance. So the longer cable has greater resistance. Because you've got a greater resistance, the charging current will be less. And so the time taken will be longer. A student owns 3 electronic devices. Each electronic device stores a different amount of charge. The table gives some information about the charge stored by the electronic devices and how often they need to be recharged. The power bank stores a maximum charge of 26.8 amp hours. The student needs to take these 3 electronic devices on a school trip for 1 week. Determine whether the maximum charge of the power bank is enough to recharge the batteries of the 3 electronic devices during the school trip. This is a really nasty paper. So let's do some maths here. If this is going to need recharging once every day, we need to do 2.4 times 7, which equals 16.8. Total those up. So total charge needed is 27.8. This is greater than the power bank's charge of 26.8. Therefore, the power bank cannot recharge all the devices. However, the power bank could be recharged Static electricity is all about the build-up of charge. And when we talk about charge, we're talking about either the build-up of positive or negative charge. Now, the only way we can build up charge is through the transfer of electrons. So if an object gains negative charge, it has gained negatively charged electrons. If the object becomes positively charged, it means it's lost negatively charged electrons. For an object to become charged, it needs to be an electrical insulator. By definition, it can't have any free or delocalized electrons. So a good example of an electrical insulator is plastic, wool, wood. Metals are electrical conductors, and that's because they have a sea of delocalized electrons where the electrons are free to move. As a result, you can't get a buildup of charge on a metal. So how does an object become charged? Think about when you were little and you got a balloon and you charged it on your head. What did you do? Well, you rubbed that balloon really hard on your head, and actually what you were doing was there was friction between the balloon and your head, which caused the transfer of electrons, meaning that the balloon became either positively or negatively charged, depending on whether it lost or gained electrons. How can we use a simple experiment to show that an object has become charged? Well, say we charged a plastic rod by rubbing it with a cloth. You could then hold that charged rod near a stream of water and you'll find that that water deflects. If you have 2 objects which are oppositely charged, they'll clearly attract each other. If you have 2 objects which have the same charge, then they will repel. One equation that comes up fairly frequently is Q equals IT. Remember, Q stands for charge measured in coulombs, I stands for current, and T stands for time. So to find charge, you do current times time. Make sure your current is in amps and your time is in seconds. If you see a child slide down a plastic slide, Due to friction between the slide and the child's hair becomes negatively charged and those hairs repel, causing the hair to stand on end. There are some uses, though, of electric charge. One of them is using electric charge to paint a bike. Historically, we just use a paintbrush, but that gives quite an uneven finish and it wastes a lot of paint. What you can do instead is give the bike frame a positive charge. You could give the paint in a paint sprayer a negative charge. All those paint droplets will therefore repel each other and form a fine mist. They'll then be attracted to the oppositely charged bike frame, so you get a really even finish and it ensures that very little paint is wasted. An electrostatic precipitator is used to clean the flume gases from factory chimneys. So obviously lots of factories burn fossil fuels and they'll be releasing particulates into the atmosphere, including soot. Now, we don't want the soot going into the atmosphere because it causes global dimming, it causes asthma, it's not good for people with bronchitis. So the way in which we can remove the particulates from the waste gas is by using two charged plates which have the opposite charge to the waste particulates. Therefore, the particulates stick to the plates, leaving all the waste gases clean so they can go into the atmosphere, and then the plates are regularly cleaned to remove any soot stuck to them. There are some dangers associated with static electricity. One well-known one is aeroplanes. So aeroplanes become charged, again due to friction, when they fly through the clouds. So when they land, they are still charged. And that's because they have rubber tires. Now, what can happen when the fuel tanker comes out is that a spark can jump in order to drain that excess charge. The spark can jump from the plane, and technically it could jump to the fuel tanker, which would cause a huge explosion and fire. To prevent this danger, don't worry, planes use an earthing strip, so a big metal strip when they land to help drain excess charge to earth. It's very similar to how an earth wire works inside a plug. This question is about electrostatics. A polythene rod is rubbed with a cloth which causes both the rod and the cloth to become charged. Which of these is the force that causes the rod and the cloth to become charged? That's going to be friction, because you're rubbing the cloth on the rod. The polythene rod becomes negatively charged. Which of these statements explain how the rod becomes negatively charged? Now, the only particles which can move are electrons. Remember, electrons are negatively charged, so by definition, if it's negatively charged the rod, it must have gained electrons. The answer is A. A student has rods made from different materials. The student rubs each rod the same way with a cloth. The student measures the charge gained by each rod 3 times. Here's a table of results. One of the readings for the polythene rod is anomalous. Circle the reading which is anomalous, it must be this one. State how the student should deal with the anomalous result. It's only worth 1 mark. I'm just going to write that you should discard the anomaly when calculating a mean. Calculate the mean charge for the polythene rod. So let's follow what I just said. We're discarding the minus 80. So we just need to add up these two numbers and divide by 2. Describe how the student could use the rods to demonstrate that there are 2 different types of electric charge. Hold the charge rods near each other. Like charged rods will repel. Oppositely charged rods will attract. There are 2 main types of wave, transverse waves and longitudinal waves. Do make sure that you can define both of these terms, as this comes up super regularly. So transverse wave is a wave where vibrations occur at right angles to or perpendicular to the direction the wave is travelling. Most waves are transverse waves, including water waves and all of the electromagnetic spectrum. So that includes waves like gamma waves, visible light, infrared, ultraviolet. Now, a longitudinal wave is a wave where vibrations occur parallel to the direction the wave is travelling. The best example here is your sound wave, but also P waves in an earthquake. If we look at these wave diagrams, you can see that the top wave represents a transverse wave, the bottom wave represents a longitudinal wave. So transverse wave is your typical wave. The longitudinal wave you might have seen modelled as a slinky. You have areas of high pressure, which we call a compression, and areas of low pressure, which we call a rarefaction. The distance between two compressions is known as a wavelength. Let's look more closely at a transverse wave. Now, you'll sometimes see a longitudinal sound wave looking very like a transverse wave, and it is possible to model them in a similar way using an oscilloscope, which we'll talk about a little later. But the main thing I want you to pull out here is the various parts of a wave. The distance from the midpoint to the peak or trough is known as the amplitude. The distance between two peaks or two troughs is known as the wavelength. And make sure you can distinguish one complete wave. Other key terms include wave frequency. This is measured in hertz. It's the number of waves per second. The time period is the time for one wave. It's usually measured in seconds. To calculate wave speed, you need to use the following equation, which states that wave speed equals frequency times wavelength. Frequency equals 1 over time period. If we consider the term frequency again, so it's the number of waves per second, clearly if the peaks of the wave get closer together so that the wavelength decreases, you're going to have a higher frequency. Quite simply, you'll have more waves per second. If those peaks move apart, you increase your wavelength, meaning you'll have a lower frequency. All waves have the following in common: they can be reflected and refracted and diffracted, and they all transfer energy. A teacher demonstrates different types of waves. He uses a spring to demonstrate longitudinal waves. Draw arrows on the diagram to show the direction in which the teacher moves his hand. So we need to show him moving his hand parallel in this direction and this direction. Give an example of a longitudinal wave, the sound wave. The teacher then demonstrates transverse waves. He fixes a vertical rod in a pond. He places a small wooden ring on the rod. The ring floats on the water and moves up and down the rod as waves go past. On the diagram, draw a line to show one wavelength. Label your line W. So we want the distance between two peaks. Draw that nice and accurately. The distance between P to Q is 5 centimeters. Determine the amplitude of the wave. So we know that this is 5 centimeters. Let's draw our equilibrium line. It runs halfway. So that means our amplitude is 2.5 centimeters. The wooden ring reaches point P every 15 seconds. Calculate the frequency of the wave and give the unit. So 15 seconds is our time period, the time for one wave. Frequency is given by the equation. Frequency is 1 over period, and the unit of frequency is hertz. We explain how the movement of the wooden ring demonstrates that this wave is transverse. Really, you just want to define what a transverse wave is here. Vibrations occur perpendicular to the direction the wave is travelling. The wave shown is a water wave. Give a different example of a transverse wave. Just pick any of the electromagnetic waves. I'm going to go in with gamma. Let's consider the Doppler effect now. The Doppler effect is the change in frequency and wavelength caused by relative movement of the source of wave or observer. But what do we really mean by that? Well, a really good example is if we take an ambulance. Have you ever wondered why an ambulance sounds higher pitched, so higher when it comes towards you, and then lower pitched when it moves away from you? Do you remember that how high a sound is, the pitch of a sound, is highly related to the frequency? The higher the frequency of the wave, so the more waves per second, i.e. the shorter the wavelength, the higher the pitch. If those wavelengths increase in length, which means you have a lower frequency, then you will have a lower pitch. Make sure you're very clear on that. So let's use the ambulance to illustrate the Doppler effect. As the Doppler effect definition states, it's all to do with objects and observers' relative position to each other. So the ambulance starts driving towards you. There are lots of sound waves being given off that ambulance siren. Because the ambulance is driving towards us, you can think that the sound waves get squashed. It means that the peaks of the sound wave move closer together, reducing the wavelength and therefore increasing the frequency of the sound wave. Remember, I said that high frequency means a higher pitch, and that's why the siren of the ambulance sounds higher to us. What about when the ambulance drives past us and starts moving off into the distance? Well, this time what you find is that the wavelength increases, which means the frequency of the sound wave decreases, and as a result you hear a lower pitch. This is obviously all based on the equation wave speed equals frequency times wavelength. The wave speed, the sound wave speed, is unchanged, but due to that change in wavelength, you've altered the frequency and therefore altered the pitch. The Doppler effect is also in evidence with light waves. Redshift is a really good example of the Doppler effect. Remember that light from distant galaxies appears redshifted, it looks redder. That's because those distant galaxies are moving away from us, therefore the wavelength of light is increasing. As a result, it appears more red to us. If those galaxies were moving towards us, the wavelength would decrease, and therefore that light would appear more blue. A buzzer is an electrical device that produces a sound. The frequency of a sound produced by the buzzer is 1400 Hertz. State the formula linking speed, frequency and wavelength. Wave speed equals frequency times wavelength. Sound travels at the speed of 340 meters per second in air. Calculate the wavelength. It's up to you if you rearrange first. I prefer not to. Sub in the values. Solve for lambda, which is wavelength. So do 340 divided by 1400 to get 0.24. Two students use this method to investigate sound from a moving source. Student A connects a piece of string to the buzzer. She spins around so the buzzer moves in a horizontal circular path. She spins around at a slow speed. She then spins around at a high speed. Student B stands several meters away from student A. The sound heard by student A is different to the sound heard by student B. Discuss the differences in the sounds heard by student A and student B. Let's go in with the most straightforward first mark, which is that clearly because student A is closer to the buzzer, the sound will be louder. Then if you think about the fact that that buzzer's moving in a circle around student A, because it's equidistant, it's always the same distance away from her, it will always have the same pitch. Now we need to consider this from the Doppler effect point of view for student B. So what happens when the buzzer is here and it's closer to student B? Remember those sound waves? The sound waves will be closer together when the buzzer is closer to student B, meaning that the wavelength is reduced. Because wave speed remains constant, let's just check it out. If that remains constant, if this wavelength is reduced, clearly the frequency has to increase, and so when the buzzer is closer to student B, then it will have a higher pitch. And I'm going to write that right now. So we're going to say that the frequency increases, meaning the pitch increases. When the buzzer is further away, I'm not going to repeat that science, I'm just going to say that the pitch is lower, and I'll just explain why to you separately. So this time when the buzzer's on this side, the wavelength has increased, so lambda has increased, wave speed stays the same, and therefore the frequency must decrease, meaning the pitch has decreased. Let's really point out that both the pitch and volume vary for student B. Just a small offshoot of this topic, so a little more on sound waves. Remember that we said that sound waves are longitudinal, and so they travel as a series of rarefactions and compressions, which looks something like this. But it's also really useful to show them more as a transverse wave, and we can use an oscilloscope in order to view our sound waves, as it says here in my revision guide. So it converts the sound waves detected by a microphone into visible waves on a screen, and those waves will appear as transverse waves on the screen. If they ask you about the various settings and how you actually use an oscilloscope to measure the frequency of a sound wave, so remember that's the number of waves per second, So first of all, we need a way of detecting the sound wave, which is the role of the microphone. We connect that to the oscilloscope. Believe it or not, you get a mark for adjusting the oscilloscope to get a steady trace, which means it's not a wobbly line. We need to make sure that we can see at least one complete wave cycle, which means at least that much of a wave. That is one complete wave cycle. Then we need to count the number of squares in the x direction in order to find the time period of a wave. I promise I'll show you how to do that on a past paper question. It's so much more straightforward if I actually show you one with proper graph paper. And then we can use this formula, which is frequency equals 1 over time period, to find the frequency of the wave, the number of waves per second. I promise, this will become more straightforward. We've already mentioned previously, but remember that the pitch of a sound is all to do with how high or low that sound wave is, and it's very tightly linked with the frequency of the wave. So if we look here, we can see that this wave here has a much shorter wavelength. It's much higher in frequency, so that will sound very high in our ears. Amplitude is linked to the volume of the sound wave, so the greater the amplitude, the louder the sound. So the greater the distance from the equilibrium point to the peak, the greater the amplitude, the louder the sound. An oscilloscope can be used to determine the frequency of a sound wave. The diagram shows an oscilloscope trace of a sound wave. Calculate the period of this sound wave. So you need to know that period means time for one wave, and that a complete wave looks like this. So here we have 2 complete waves. So make sure you're just measuring the time for one of those waves. I know I'm going in the x direction because look, there's my time unit. I'm told that 1 square in the x direction is 0.25 milliseconds. So how many squares make up one wave? It's 4. And then be careful with units. They want your answer in seconds, so you need to divide that by 1,000. And that is how you get 3 whole marks. So they will expect you to do quite a lot there. Calculate the frequency of this sound wave. We're using the equation frequency as 1 over time. Luckily, our time is already in the correct unit, so we just do 1 over 0.001, and you'll get an answer of 1,000 Hertz. The electromagnetic spectrum is a family of waves. These are all transverse waves, so remember your definition of a transverse wave. It's one where vibrations occur perpendicular to the direction the wave is travelling. Now you need to learn the order of waves. It doesn't matter where you start. I prefer to start from the longest wavelength, which has the lowest frequency, and work my way down until we reach the shortest wavelength with the highest frequency. So based on that, we start with radio waves, followed by microwaves. Then we have infrared radiation, visible light, ultraviolet, X-rays and gamma rays. So they could provide you with some kind of missing blanks in the question and ask you to fill in which wave sits there. So it is important that you do know the order. But what about the various uses and dangers associated with each of these waves? So if we start with radio waves, they're used in communication. Microwaves, the most obvious use is that they're used in microwave ovens. The microwaves vibrate water molecules found within food, increasing the temperature of the food. So obviously one danger associated with microwaves is this heating effect. Microwaves can also be used in communication, satellite communication specifically. Infrared radiation now this is a third type of wave which can be used in communication. The other waves include the radio waves, the microwaves, and even visible light. Infrared waves are used in our remote controls. Infrared radiation you'll have also met in the energy transfers topics. In effect, it is heat. So you can also use infrared radiation in cooking. Our toasters give off infrared radiation. Our typical conventional ovens give off infrared radiation. And as a result, a danger associated with this type of wave is that you can suffer from skin burns if you touch something which is too hot. Infrared radiation is also used in night vision goggles. Visible light now used in photography and optical fibers. Ultraviolet or UV light, now this can cause skin cancer, sunburn. We find it used in fluorescent lamps, sun tanning beds. We can also use UV to detect forged banknotes. X-rays and gamma rays now, these are both types of ionizing radiation. They're both very high frequency. They can cause cell mutation, which may lead to cancer. X-rays are used in medical imaging, so we can see inside our bodies. Gamma rays can be used to sterilize surgical equipment as well as treating cancer patients. Obviously, those gamma rays need to be directed to a very localized spot in the person's body because otherwise they can be fairly dangerous, as I've already mentioned. Now, all EM waves are transverse waves. They all transfer energy. They travel at the same speed in a vacuum, which is 3 times 10 to the 8 meters per second. They can be reflected, refracted, and diffracted. The photograph shows infrared heating lamps being used to harden fresh paint on a car, give a harmful effect of infrared waves. It even says here that the heating lamps are used to basically dry the fresh paint. So obviously they're hot, so you can get a skin burn if you get too close. The heating lamps produce visible light waves in addition to infrared waves, give 2 similar properties of visible and infrared. They travel at the same speed in a vacuum. They both transfer energy. Give 2 differences. So the visible light has a shorter wavelength. Visible light has a higher frequency. The infrared heating lamps are placed 1.5 meters from the car. Calculate the time taken for infrared waves emitted from a lamp to reach the car. And here's their speed. So we can see that time is distance over speed. 1.5 divided by 3 times 10 to the 8 gives us a time of 5 times 10 to the minus 9 seconds. The light and sound topic. Remember that light waves are transverse waves. Their vibrations occur perpendicular to the direction the wave is travelling. We're often asked to draw the path that a light ray takes through an object, such as a glass block, and it's useful to draw a normal line in order to do that. A normal line is simply a line drawn at 90 degrees to the surface of the object. If we use our glass block as an example, the light ray which hits the glass block is known as the incident ray, and the angle between the incident ray and the normal line is known as the angle of incidence. It's also possible to draw a normal line on a plane mirror. A plane mirror is simply a flat mirror. In this case, the light ray hits the plane mirror and then it bounces off the plane mirror. We call this bouncing ray the reflected ray, and the angle between the normal and the reflected ray is known as the angle of reflection. Now, the law of reflection states that the angle of incidence equals the angle of reflection. Refraction is different from reflection. Whereas reflection you can think of a light ray bouncing, refraction is all to do with rays changing direction when they enter a new medium, and that's due to a change in the wave's speed. So if we take our glass block and we shine a light ray at the glass block, you can draw the normal as usual to make sure that you can measure the angle of incidence. You will find that that ray is deflected as it enters the glass block. It doesn't continue in a straight line, and that's due to refraction. As it enters the glass block, the ray slows down and it changes direction towards the normal. Then as the ray leaves the glass block, the ray speeds up because it enters air, so it can travel faster in air. You will find that that ray changes direction again, and this time it bends away from the normal. Now, if the ray strikes the boundary at 90 degrees, you find that no refraction occurs and the ray continues through the block without changing direction. Let's look at a slightly more complicated version of refraction. So we're still looking at light rays. This time we want to consider the wavefronts. So let's take a look at the orange line first of all. We're going from air to glass, so as you'd expect, as the light ray moves from air to glass, because it slows down, it changes direction towards the normal. See, it's not carrying on in a straight line, it's moving towards the normal. And then as it leaves the glass, the ray speeds up, it moves away from the normal. If you were to add wave fronts, you want to be drawing those at 90 degrees to the direction of travel. So look, these are drawn at 90 degrees compared with our orange light ray. Just be very careful. As they enter the glass block, keep the rays running at 90 degrees to your light ray and you won't go wrong. And again, they'll change direction again here. Because they're slowing down as they enter the glass block, look, the wavefronts get closer together. When they're travelling faster, the wavefronts move further apart. As a result, the wavelength has increased. The refractive index now, this is the extent to which light is refracted when it enters a medium. A more dense medium has a greater refractive index, and therefore you see a greater refraction of light. There's an equation for calculating refractive index. We usually assign n as refractive index, so refractive index n equals sine I over sine r. That means you need to use the sine button on your calculator. You input sine plus your angle of incidence, and then you divide it by sine angle of refraction. So do make sure you've got a protractor in your exam and that you can accurately measure the angle of incidence and the angle of refraction. Sometimes they ask you to describe an experiment to investigate the refractive index of a glass block. What you need to do is get a ray box. You need a glass block which you draw around on a piece of paper. Make sure you've drawn a normal on your piece of paper. You shine a light ray at your glass block and you follow the path that that ray takes in the glass block. You draw it on your piece of paper, and that will give you an angle of refraction which you can measure. Keep changing your angle of incidences, so keep moving that light ray box so that you get a whole range of angles of refraction. It's then possible to plot a graph of sine I, so take your angles of incidence, make sure you plug them into the calculator, sine 15 degrees, sine 20 degrees, etc. Do the same with the angles of refraction, so sine R, and then you'll have a graph. By finding the gradient of the graph, remember gradient is change in y over change in x. In effect, you're doing sine I divided by sine R, and that will tell you the refractive index. Another angle I want you to be aware of is the critical angle. We can calculate the critical angle using the following equation, which is sine C equals 1 over n. N stands for refractive index. C is your critical angle. I'll show you a quick example. So find the critical angle if the refractive index is 1.5. So write your equation, sine C equals 1 over n. Sub in your refractive index. Work it all out, so sine C equals. Then just be careful with your calculator. What you want to do to find C, you want to do inverse sine. So it's sine to the minus 1, 0.6 recurring. Practice using your calculator. Press the shift button, sine, type in 0.6 recurring, and you should get a critical angle value of 42 degrees to two significant figures. Now, you will find that something called total internal reflection occurs if your angle of incidence is greater than the critical angle. Something else must be true for total internal reflection to occur. Your ray must be moving from a more dense to less dense medium. Or you could put that in other words, you could say that the light ray must travel from a higher refractive index substance to a lower refractive index substance. If this isn't happening, even if you've got an angle of incidence greater than the critical angle, you won't see total internal reflection occur. So let's look at three different scenarios. The first one is when the angle of incidence is less than the critical angle. We haven't met our requirement for the angle of incidence being greater than the critical angle, so as a result, total internal reflection does not occur. Instead, you get a little bit of internal reflection and mostly refraction, but you don't get total internal reflection. You do get some refraction. What happens if we increase the angle of incidence so it equals the critical angle? You'll get a small amount of reflection, but most of it will be refraction which occurs along the boundary, so between the glass and air interface. If we increase that angle of incidence further so that it is greater than the critical angle, yes, we've got total internal reflection taking place. That light ray is staying inside the glass block. One use of total internal reflection is optical fibres. You find that your core of your fibre is made out of glass with a high refractive index. The cladding is made out of glass with a low refractive index. And what that ensures is that total internal reflection occurs along the length of the optical fibre. We can use optical fibres in endoscopy, so that's keyhole surgery when surgeons make very small incisions to view inside your body to remove small obstructions. It can also be used in communication. Diagram 2 shows what can happen when a light ray travelling in glass meets the boundary with air. The wavefronts are not shown in this diagram. Add the normal to diagram 2, so that's a line drawn at 90 degrees to the boundary. Measure the angle of incidence in diagram 2. So here we have the incident ray, which means that this is the angle of incidence. You need to use your protractor carefully here. You'll find that that is 55 degrees if you've measured it accurately. The glass has a refractive index of 1.6. Calculate the critical angle of the glass air boundary. So we're using this equation. N is our refractive index, so sub in 1.6. So sine C equals 0.625. And then remember, we need to press shift sine to get inverse sine. And when you put that into your calculator, you'll get a value of 39 degrees. We explain the path of the light ray shown in diagram 2. This is absolutely total internal reflection. We can see how that light ray is being internally reflected, and that therefore means that the angle of incidence must be greater than the critical angle. And this occurs because the ray is travelling from a high to a low refractive index. Let's go through all the different types of energy store. So your chemical energy store is what's found in things like food, fuel and batteries. A car obviously uses up its chemical store as it burns through its fuel. Kinetic energy is all to do with moving objects, so a car moving along the road, a person running. Gravitational potential is to do with objects being at height. They gain a gravitational potential store. The higher up they go, the greater the gravitational potential store, but according to this equation, gravitational potential energy equals mass times gravitational force times height. So obviously, as the object increases in height, that GPE will increase. Elastic potential is energy stored when an object is stretched or squashed. Springs and elastic bands contain elastic potential energy. You'll come across that in Hooke's law, which remember is all to do with the directly proportional relationship between spring length and load added to spring. Nuclear energy is to do with energy stored in the nucleus of an atom. Radioactive uranium fuel contains nuclear energy. Thermal or heat is the total kinetic and potential energy of the particles in an object. Anything hot contains thermal energy. Magnetic energy store is energy stored when repelling poles of a magnet are pushed closer together or attracting poles are pulled further apart. Electrostatic is the energy stored when repelling charges are pushed closer together or attracting charges are pulled further apart. We find electrostatic energy in thunderclouds and our Van de Graaff generators. Remember, you might have done this at school. You touch that charged dome and it causes your hair to stand up on end. Increasingly, they like to ask you about how energy can be transferred. That can be one of 4 ways. Mechanically, which is when a force moves an object through a distance. Electrically, that's the movement of charges due to a potential difference between 2 areas. By heating, that's due to a temperature difference caused electrically or by a chemical reaction. And radiation. So we're talking really about energy being transferred as a wave, such as the electromagnetic waves, visible light and infrared. The conservation of energy states that energy cannot be created or destroyed. It can only be converted from one form into another. Now we like to often calculate efficiency, and efficiency is useful energy output divided by total energy input. You might also see this equation written as useful power output divided by total power input times by 100 to get it into a percentage. And a Sankey diagram is used to show how the energy in a system is transferred. So we often look at wasted energy and useful energy. I'm going to show you some calculations now using these equations. A panel of solar cells converts energy from the sun into electrical energy. It was calculated that for every 200 joules of energy from the sun, 176 joules of energy is wasted by the solar cells. Calculate the efficiency of the solar cells. So always write out your equation. So efficiency equals useful energy output over total energy input times by 100. So we know that the energy input is 200 joules. Be careful with your useful energy output. We can see that 176 of those 200 joules is wasted, which means we can infer that 24 joules was usefully transferred. So 24 is your useful energy out. Put that into your calculator, and our efficiency is really only 12%. Draw a Sankey diagram for the energy transferred by the panel of the solar cells. So draw your Sankey diagram as accurately as you can. The width of the arrows is very important. So I'm going to call this my input energy, which was 200 joules. My useful energy is an arrow coming out to the right like this. So this, remember, was 24 joules of useful energy, and we want to show a much wider wasted energy. So here's our wasted energy arrow. Important equation is work done equals force times distance. Bear in mind that the unit of work done is joules, which always throws some people off. Joules, remember, is the same unit we use for energy. Force is measured in newtons, and distance, the standard distance unit, is meters. So we'll look at this worked example. A force of 20 newtons is required to lift an object 1.25 meters. Calculate the work done on the object and the useful energy transferred to the mass. So work done, always write out your equation, equals force times distance. Our force is 20, our distance is 1.25, all the units are fine, so the answer here is 25 joules. So that's the answer to part 1. And what is the useful energy transferred to the mass? They want you to realise that due to the fact that the units of work done and energy are the same, the useful energy transferred, assuming 100% efficiency, will also be 25 joules. Then we have the equation gravitational potential energy is mass times gravitational field strength times height. So our unit for energy, remember, is joules. Our unit for mass is kilograms. Gravitational field strength, you do need to remember that number, it's 10. Height is measured in meters. Another important equation is kinetic energy equals half mass times velocity squared. I wouldn't worry about rearranging that equation when it comes to using it. If you're asked to find something like V, it's much easier if you just sub in the numbers in the same place, and I'll show you some examples later on. Power now. Now power is the rate of energy transfer, or the rate of doing work, the rate of work being done. The equation for power is work done or energy over time taken. So it could be arranged like we see it here, or it could also be power equals energy over time. The units of power are watts. We'll go through this example. A toy car of mass 1 kg slides down a slope. If the top of the slope is 2 meters higher than the foot of the slope, how fast will the car be moving when it reaches the foot? Assume that all of its GP is transformed to KE. So the first thing we need to do is work out the gravitational potential energy. So we use the equation mass times gravitational field strength times height. Our mass was 1, G, remember, is 10. The height we were told is 2. So that GPE is going to be 20 joules. Then it wants us to find out how fast will the car be travelling when it reaches the foot. We have to assume that all that gravitational potential energy is transferred to kinetic energy. Let's write our kinetic energy equation. So according to this, we can sub in 20 joules as being our kinetic energy. The mass stays the same of 1 kilo. We're after V. Simplify the right-hand side. To get V squared on its own, you need to divide 20 by 0.5 and then obviously square root to find V. So the speed it's travelling when it reaches the foot of the slope is 6.3 meters per second. Now we're going to do an example involving power and work done. So a large elastic band is stretched 34 centimeters by a student. Immediately I'm going to pop that into meters so I don't have an issue with my units. The average resistant force is 23 newtons. Calculate the work done when the elastic band is stretched once and the average power of the student when the band is stretched 15 times in 1 minute. So let's do part 1. Work done equals force times distance. We're told that the force is 23 newtons. I've already converted my distance into meters, so the work done is 7.8 joules. How about finding the average power when the band is stretched 15 times in 1 minute? We will want to use the equation power equals work done over time. But we really need to find what the time is for one stretch. So if the band stretches 15 times in 1 minute, that's 60 seconds. So if it takes 60 seconds to stretch the elastic band 15 times, clearly it takes 4 seconds to stretch it once. The work done we just found out. And our final answer is 2 watts. A large rock of mass 50 kilograms is lifted 80 meters to remove it from the mine. State the equation linking gravitational potential, mass, gravity and height. So GPE equals mgh. Calculate the gain in gravitational potential energy when the rock is lifted 80 meters. Always state your equation, label everything. That's our height. There's our mass. Gravity, remember, is 10. You need to remember that. So we do 50 times 10 times 80. And then don't forget your units, which is joules. So our answer is 40,000 joules. State the work done in lifting the rock. They want you to recognize that energy and work done have the same unit. It's only worth 1 mark. It's the same answer as before, 40,000 joules. A flying squirrel is an animal that can glide through the air. It spreads out its limbs to stretch a membrane that helps it to glide. The mass of the flying squirrel is 0.19 kg. It climbs 17 meters up a tree. State the equation linking GPE, mass, gravity and height. GPE equals mgh. Calculate the GPE gained by the squirrel. So we just do 0.19 times 10 times 17. Our answer is 32 joules. State the amount of work done against the force of gravity by the squirrel during this climb. Look how often these questions come up. The answer is just 32 joules. The flying squirrel glides from P to Q with a constant velocity of 13 meters per second. Add labeled arrows to the diagram to show the direction of the forces of weight and drag acting on the squirrel. So remember, the squirrel's weight will act downwards. Drag acts against the direction of motion, so it'll be acting in this direction. State the equation linking KE, kinetic energy, mass and velocity. Kinetic energy is half mass times velocity squared. Calculate the kinetic energy of the squirrel as it glides. So what is the mass of the squirrel? It was 0.19. What was its velocity? It was 13. Put that into your calculator and you'll get an answer of 16 joules. An underground train enters a station. The mass of the train and its passengers is 250,000 kg. The total kinetic energy is 18 megajoules. I'm just going to get that into joules, the standard unit, by timesing by a million. State the relationship between kinetic energy, mass and velocity. KE equals half mv squared. Calculate the velocity of the train as it enters the station. Now, with this equation, it's pretty nasty, so actually I never bother to rearrange it. I just sub in my numbers. Our kinetic energy, remember, is this huge number. I've already sorted out the units. Our mass was 250,000, and we're after v squared. Simplify. Divide both sides by 125,000 to get v squared equals, and then square root to get a final answer of 12 meters per second. The photograph shows a small aeroplane of 600 kg. This aeroplane has an electric motor powered by fuel cells. Fuel cells use hydrogen gas and provide an electric current. When the aeroplane is working, the energy changes are, so we know that we've got an electric motor powered by fuel cells. So within the fuel cells, we have a chemical energy store, then it's being converted to an electrical store, and then obviously the plane is flying, so it's kinetic. So the answer here is A, because we're going from chemical to electrical to kinetic. The velocity of the aeroplane is 28 meters per second. State the equation linking kinetic energy, mass and velocity. Half mv squared. Calculate the kinetic energy of the aeroplane. So sub in your numbers carefully. We were told that the mass of the plane was 600. Do 28 squared. Multiply those all together to get 240,000 joules to two significant figures. The aeroplane takes off and climbs to a height of 1,000 meters. State the equation linking GPE, mass, G and height. GPE equals mgh. Calculate the gravitational potential energy gained by the aeroplane. So again, that mass was 600. G, remember, is 10. Our height is 1,000. Our answer here is 6 million joules. The fuel cells provide a maximum total power of 24 kilowatts. I'm just going to times that by 1,000 to get it into watts. That's our power. The aeroplane also carries a large rechargeable battery. Show by calculation that the aeroplane needs this extra source of power to climb to 1,000 meters in 3 minutes. So we need to work out how much energy that aeroplane needs. So we're going to use energy equals power times time. Power is 24,000. Time, we're told it's 3 minutes. Get that into seconds by multiplying by 60 because we need the standard unit in order to ensure that our energy calculated is joules. Do 24,000 times 3 times 60 to get 4,320,000 joules. So clearly we need that extra large rechargeable battery because the energy supplied is less than the energy required. So we need that extra boost. So just point out that value is less than the 6 million joules. The photograph shows the equipment used for generating electricity from renewable sources. Complete the sentences using words from the box. The panel of solar cells transforms, that will be light energy into electrical energy. The wind turbine transforms something energy into electrical energy. The wind is blowing the wind turbine blades, so it's actually going to be kinetic because those turbine blades are moving. On a windy day, the wind turbine transfers 78 watts of power. State the equation linking power, energy transferred, and time. Power equals energy transferred divided by time. Calculate the amount of energy the turbine transfers in 10 seconds. So E equals P times T. Just do 78 times 10 to get 780 joules. Supermarkets use conveyor belts to move shopping at the till. The diagram shows a carton of milk being pulled along by a horizontal conveyor belt. The horizontal force on the carton from the belt is 1.7 newtons. The carton moves a distance of 0.46 meters. State the equation linking work done, force and distance. Work done equals force times distance. Calculate the work done moving the carton. Our force was 1.7 newtons. Our distance is 0.46. So our work done is 0.78 joules. State how much energy is transferred to the carton. It's the same unit, so it's 0.78. The belt stops suddenly and the carton falls over. How does this affect the kinetic energy of the carton? Well, obviously because the belt's stopping and the carton's falling over, the kinetic energy will decrease. Why does falling over reduce the gravitational potential energy of the carton? Think about an appropriate equation here. If GPE equals mass times gravity times height, if the carton falls over, the height decreases, meaning GPE decreases. question is about an electric fan. A battery supplies a voltage of 12 volts and a current of 0.2 amps. The fan is switched on for 12 seconds and the fan gains 25 joules in its kinetic energy store. Calculate the efficiency of this energy transfer. So we need to combine both our efficiency equation as well as our electricity equation, which states that E equals IVT. So just to give you more detail, remember that efficiency is useful energy output divided by total energy input. Because it's a fan, obviously we want the air to be moving, so this 25 joules right here must be the useful energy output. We can't calculate the efficiency until we've got the total energy input, and that's where this equation here comes in, E equals IVT. So we know that the current was 0.25, the voltage we were told was 12, the time is 12 seconds, luckily everything's in the correct unit, so you'll get 36 joules as your total energy input. So I'm going to pop that there. Because they want the final answer as a percent, I'm going to multiply it by 100. And when you've done 25 divided by 36 and multiplied it by 100, you get an efficiency of 69%. FunCube 1 is a satellite that was launched into orbit around the Earth. The rocket carrying FunCube 1 burns fuel to accelerate upwards. As the rocket burns fuel, the energy in its chemical store reduces because it's using up the fuel. The energy in its kinetic store and gravitational store changes. State how the kinetic store of the rocket changes as the rocket burns fuel. Well, it's going to be moving faster, so it's going to increase. State how the gravitational store of the rocket changes as the rocket burns fuel. Well, it's going up, which means it gains height. GPE equals mgh. We've increased our h value, so our gravitational store will also increase. The rocket engine stops burning fuel. The rocket continues to go further away from the surface of the Earth. The table gives some statements. Add ticks to the table to show which two statements are correct. Will the gravitational store increase? Yes, we've just said that. In terms of what happens to the kinetic store, because the rocket stops burning fuel, it's actually going to reduce. FunCube 1 goes into a circular orbit above the surface of the Earth. State the name of the force responsible for keeping FunCube 1 in orbit. It's gravitational force. FunCube 1 has an orbital radius of 7,100 kilometers and an orbital period of 5,800 seconds. Calculate the orbital speed in kilometers per second. So here's your equation. They've been nice with units for once. We don't need to change anything. We're trying to calculate v, so we do 2 pi times the orbital radius, which was 7,100, divided by the time for one orbit, which was 5,800, to get an answer of 7.7. Now, how may thermal energy transfer occur? Well, it can occur by conduction, convection, or radiation. We'll go through each of these types of heat energy transfer in turn, starting with conduction. So conduction occurs best in metals, and that's because they have delocalized electrons which are free to move. Conduction works better in solids compared with liquids, compared with gases, and that's because the particles in solids are closer together. Gas is a poor conductor and is therefore a good insulator. Let's try and understand why a metal spoon feels hot when placed in a hot coffee after a short amount of time, and that's all down to conduction. So heat causes the particles in the solid to gain kinetic energy. This causes them to vibrate more, and because the atoms are close together, energy from the increased vibrations is passed on to the next door atom, and so on and so forth. In a metal, conduction occurs really quickly due to the delocalized electrons which are able to move freely throughout the metal. Convection occurs in fluids, so liquids and gases. Let's use the example of a radiator in a room to understand how convection currents are set up. So first of all, we turn on our radiator. It heats up, heating the air molecules above. This causes the air molecules to vibrate more, they gain kinetic energy, and they spread out. The air expands and becomes less dense. This hot air rises, and then cooler, denser air falls down to replace it, therefore setting up a convection current as the process repeats again and again. Infrared radiation, remember, is a type of electromagnetic wave. Colour is very important with infrared radiation. We always want to talk about whether a particular surface is a good reflector, emitter, or absorber of infrared radiation. So starting with black matte substances, you'll find that these are good absorbers of infrared radiation. People like me with very dark hair, you'll find that on a hot day, when you're in the sun, your hair gets very hot very quickly, and that's because dark colours are a good absorber of infrared radiation. Black matte substances are also good emitters of infrared radiation. White shiny surfaces now, these are poor absorbers and poor emitters of infrared radiation. Instead, they're good reflectors. This is why if you think about buildings in Greece, if you've been on holiday there, why are they painted white? Because it gets incredibly hot in Greece in the summer, and white is a good reflector of infrared radiation. Remember that space is a vacuum, so how does energy from the sun reach us? Through infrared radiation. Remember, because it's an electromagnetic wave, it can pass without the need for particles. As a result, you don't get heat energy transfers by either convection or conduction in space, as you require particles for both of these processes to occur. Remember, space being a vacuum means that it contains no particles. The key to doing well in past paper questions relating to this topic is being very specific. Don't say anything about heat being trapped. You need to specify whether conduction, convection, or radiation is affected. For example, how does a woolen blanket keep you warm? Well, wool is a good insulator, a poor conductor. Wool traps air. Air is a good insulator, it's a poor conductor. How does a polystyrene coffee cup with a lid prevent the coffee getting cold? First of all, the lid prevents convection currents being set up on the top of the hot coffee, preventing heat transfer by convection. The polystyrene cup is a good insulator, poor conductor. How does a vacuum flask help to keep our drinks hot or cold? You can talk about the plastic stopper, again preventing convection currents being set up. You could say that the bottle is lined with a silver coating because silver is a good reflector of infrared radiation. You can say the bottle itself is made out of plastic because plastic is a good insulator. Do make sure that your answer is specific to the question. Before the invention of modern air pumping systems, fires were sometimes used to help ventilate mines. A fire was lit at the bottom of the ventilation shaft to make sure that fresh air flowed into the mine through the access shaft as shown in the diagram. So what happens is when you light that fire, the air molecules vibrate more, they move faster and gain kinetic energy. They spread out, the air expands and becomes less dense. The hot air rises. Cooler, denser air falls down to replace that lost air, setting up a convection current which helps to make sure that fresh air is constantly supplied to the ventilation shaft. The passage explains the movement of air in the mine. Use words from the box to complete the passage. Each word may be used once, more than once, or not at all. Air is heated by the fire and the air molecules move faster. The air expands as the molecules move further apart. The density of the air decreases and the hot air rises. Cold air flows in to replace the hot air and the process continues as a convection current. Photograph 1 shows an outdoor swimming pool. The water in the swimming pool is heated by the sun during the day. State how energy is transferred from the sun to the water. Because there's a heating effect, remember that energy transfer occurs by radiation. State what happens to the average speed of the water molecules as the water is heated. Hopefully that's nice and obvious. The speed increases. The water in the swimming pool cools down at night. Suggests why the water cools down at night. So why would the water cool down at night? It's because there's a temperature difference between the water and the nighttime temperature. The nighttime temperature must be lower, meaning that energy is transferred, or you could say that it's no longer receiving infrared radiation from the sun. Photograph 2 shows the swimming pool with a plastic cover over the water. Explain why the plastic cover reduces how much the water cools down at night. Oh, this is a real conduction, convection, radiation question. So remember, always link your answers to those specialist terms. So we're going to say plastic is a good insulator, meaning that heat losses by conduction are reduced. We can also say that the plastic cover traps a layer of air It's a little bit like how a plastic cover works on a coffee cup, keeping the coffee hot on top of the water. And what do we know about air? Air is a poor conductor. I also want to add that the plastic cover prevents convection currents on top of the water. Let's take a look at energy resources and electricity generation. We're distinguishing between a renewable resource and a non-renewable resource. So a renewable resource is an energy source that is replenished at a faster rate than the rate at which it's being used. Non-renewable resources, this is an energy source that will run out. So we're really talking about fossil fuels such as coal, natural gas, and oil. So obviously there's a lot of attention and a lot of time and money being spent on developing our renewable resource because of the advantage of them being replenished at a faster rate than the rate at which they're being used. So if we look at these different methods of generating electricity, as you can see, we've got some examples of renewable energy sources as well as non-renewable. Just to describe how they work, the wind power works by wind turning a turbine. You'll see these, they look like giant windmills. The turbine turns a generator, the generator produces electricity. Wave power is all about waves moving, floating electricity generators. Hydroelectric, you'll see these in mountainous areas. What happens is you trap water behind a dam, you allow that water to flow, it loses gravitational potential energy. As it falls, this is converted to kinetic energy, which turns a turbine, which turns a generator. Tidal power is all about trapping high tide and using it to turn generators. Geothermal is one of the most reliable types of renewable energy source. You find it in places where the tectonic plates meet, so you've got a break in the Earth's crust, somewhere like Iceland. This type of energy source uses the hot rocks in the Earth's crust to heat water to become steam, and it's the steam which turns the turbines, which turns the generator. Solar heating panels and solar cells are all to do with using the sun's energy. Fossil fuels and nuclear power are both types of non-renewable energy source. So fossil fuels we've already mentioned include oil, coal and natural gas. We burn those in order to produce steam, which turns a turbine, which turns a generator. Nuclear power, despite being non-renewable, it's not something we're likely to run out of because we only need very small amounts of things like uranium-235. We'll talk a lot more about that in the nuclear fission topic. So here's some energy transfers taking place at each type of energy resource from my revision guide. Feel free to pause the video. Looking at the various advantages and disadvantages of renewable versus non-renewable energy types, generically speaking, the renewable energies tend to be more unreliable because you need things like the wind to blow, you need big strong waves, you need the sun. The more reliable types of renewable energy source include geothermal, because that, as we know, is anywhere where there's a break in the Earth's crust, the hot rocks can heat up water, so that is a reliable renewable energy source. Hydroelectric also tends to be more reliable. Obviously, it relies on there being plenty of rain in these mountainous areas so that the water can be trapped behind the dam. In terms of the major advantages with renewable energy types, it's all to do with the lack of atmospheric pollution, comparatively speaking, with the fossil fuels. Because you're not burning substances, you're going to have less CO2 emissions, less global warming. Just to point out a few extra points, things like wind power and solar power, they do need an awful lot of space in order to actually put up the wind turbines, in order to have lots of solar panels, unless you're placing them for your own home's use on top of your roof. People make quite a fuss because of the visual and sound pollution when it comes to wind power. Hydroelectric is a real nightmare because you have to flood an awful lot of land in order to trap the water, which can lead to the extinction of species. It destroys habitats. So yeah, there are some generic advantages and disadvantages, and then it's up to you if you want to learn specific details. Fossil fuels are very reliable. They're a high density energy source, but we know they produce lots of greenhouse gases like carbon dioxide. If we look at nuclear power now, it is a reliable source of energy. You're going to have much less atmospheric pollution compared with fossil fuels. However, we have to be very careful with nuclear power plants because we produce lots of radioactive waste. which means that waste needs to be stored appropriately and securely to stop any weaponization of that waste. Because remember, radioactive material can cause cancer, it can leak into water sources. Because of the extremely long half-life, it needs storing for hundreds and hundreds of years. So this portion of my guide here really describes the disadvantages of using nuclear power. The diagram shows a fossil fuel power station. 5 stages of electricity generation and transmission are shown. We have a furnace and a boiler, which creates steam that turns the turbine, which turns the generator, connected to a step-up transformer going off to the national grid. The power station burns a fossil fuel in the furnace. Give an example of a fossil fuel. Oil, coal and natural gas are all good examples here. Which stage of the power station transfers energy from a chemical store to a thermal store? So we have our fuel containing our chemical store. It's going to be burnt. So that will be your furnace. Which stage of the power station transfers energy electrically from a kinetic energy store? That will be your generator, because remember, we move our coil of wire within a magnet in order to create our current. So that is C. Electricity can also be generated by solar farms. Energy is transferred from the sun to the solar farm by radiation. The solar farm uses photovoltaic cells to transfer this energy electrically. Discuss the advantages and disadvantages of generating electricity using solar farms. So advantages, it's a renewable energy source. We're going to have no carbon dioxide released through any kind of burning of fossil fuels, meaning less global warming. But what about our disadvantages? The main ones to do with renewable energy sources are all to do with reliability. It's an unreliable source of energy because the sun doesn't shine all the time. And remember, because of all these photovoltaic cells, we need lots of land. The density topic. This is a largely calculations-based topic. The first thing you need to be aware of is the equation for calculating density. Density equals mass divided by volume. There are several different density units. I'm going to show you how you can work it out based on the fact that the standard unit of mass is kilograms. Volume can vary. If the question says centimeters cubed, then the unit of density is kilograms per centimeter cubed. Use this equation when you're asked how to calculate the density of either a regular or irregular shaped object. So, how to calculate the density of a regular shaped object, such as a cube? We know that the equation for density equals mass divided by volume. So feel free to state that, and you should state it in your exam answer. So obviously, to find density, we need to have both the mass and the volume. So how do we find the mass? Find the mass of the object using a balance, which remember is a weighing scale. Find the volume of the object by multiplying. Think about how you find the volume of a cube, the length times width times height. So in this 1 centimeter cube, we know that to find the volume, we do 1 times 1 times 1 to get 1 centimeter cubed. Then you want to substitute your values into the equation density equals mass over volume, and you'll have your density. Don't forget to include any sensible apparatus, so use a ruler. Is an extra point you can add here. But what about if you're asked to calculate the density of an irregular shaped object, something like a stone? Clearly, you're not going to be able to find the volume by just using your ruler to find its length times its width times its height. However, still state the equation you need to use. So you're going to say that density equals mass over volume. This point will remain true, that you can find the mass of the object using a balance. But how can we find its volume? I'm going to use a Eureka can. So this is how a Eureka can works. You fill up your Eureka can, then you place your object in the can, and water will be displaced, which filters down this pipe here. You capture the water in your measuring cylinder, and then by looking at the volume of the measuring cylinder, you can infer that's the volume of the original object. So we're going to place object in Eureka can. Ensure no splashing occurs, otherwise you'll be losing some of that water. Measure volume of displaced water using a measuring cylinder. Read from the bottom of the meniscus. This is all about improving accuracy and at eye level to avoid parallax issues. So yeah, just have a look again. How are we finding the density of an irregular shaped object? State the appropriate equation, state how you find the individual masses and the volume, substitute your values in order to calculate density. What about if you're asked to find the density of a liquid? It's really straightforward. This time you're going to measure the mass of an empty beaker using a balance, pour your liquid in and measure the new mass, and then you can use your equation density equals mass over volume in order to find the liquid's density. But let's do a sum showing that we can actually use this equation. So the mass of 100 centimeters cubed of a liquid and a conical flask is 152 grams. The mass of the empty conical flask is 106 grams. What is the density of the liquid in kilograms per meter cubed? Be very careful here with your units. We know that we're finding the density. If the mass of the liquid in the conical flask is 152 grams, the empty conical flask's mass is 106, the mass of the liquid must be 152 minus 106, which is 46 grams, but our unit needs to be in kg, so we need to divide that by 1,000 to get 0.046 kilograms as our mass. Be really careful now with your volume because they want it in meters cubed, but we've been told we've got 100 centimeters cubed. To get centimeters cubed to meters cubed, this is a really nasty conversion. You want to divide by 1,000,000, and so 100 centimeters cubed is the same as 0.0001 meters cubed. So we've done that unit conversion. Put it into your calculator and you'll get a final answer of 460 kilograms per meters cubed. To calculate pressure, we can use this equation which states that pressure equals force divided by area. Here's your formula triangle. So pressure equals force over area, force equals pressure times area, area equals force divided by pressure. What about the units of pressure? Force is measured in newtons, area can be measured in meters squared, and so one of the pressure units is newtons per meter squared. You might also see pressure written as pascals or kilopascals. To convert between kilopascals and pascals, you need to times by 1,000. Let's think about the context of pressure. So, why do stiletto heels make dents in soft wooden floors? Well, if you think about it, the person's weight, their force, is bearing down over a very, very small area. So the force, remember, is their weight because that's also measured in newtons. Then you've got a very small area created by the stiletto heel. I'm not going to try and draw that because I can't draw. But what happens then is because you've got a larger number divided by a very small number, that means that your pressure value is very high. High pressure causes damage to wooden floors. Just trying to give you some context here. Why are knives sharp? Because if you think about the blade of a knife, you're bearing down a very large force when you're cutting something with the knife. The area of the knife is incredibly small, so you're creating a huge pressure which actually helps make that knife sharp. If you think about skis, you've got a very different scenario here. So again, you've got the person's weight bearing down, but the ski creates a very large area. So if you are dividing a particular weight or force by a very large area, clearly you've got a number being divided by a very large number, so that's actually going to reduce the pressure. Skis reduce pressure, meaning you don't sink into the snow. Let's do a calculation here. A student has a mass of 52 kilograms. They measured the area of their foot and calculated it to be 148 centimeters squared. Calculate the pressure in newtons per meter squared. that the student exerts on the ground when they are standing on both feet. So we've got quite a lot going on here. Start by writing your equation. Pressure equals force over area. You need to be careful. The force we need to calculate by using weight equals mass times gravitational field strength, because remember, weight and force are interchangeable because they both have a unit of newtons. So if the mass is 52, gravitational field strength is 10, the weight of this student is 520 newtons, so we can substitute that in as our force. What about the area? Well, each foot has an area of 148. There's 2 feet on a person, so we need to multiply that by 2. So we have 296 centimeters squared, but we need that in meters squared because of this unit here. So the way we do that is by dividing by 10,000. Be so careful with your units in physics. But we've done all the working out we now need to do in order to calculate that the pressure is 17,568 newtons per meter squared. Let's think about how pressure changes with altitude. So pressure at high altitude, such as the top of a mountain, maybe you're aware already, but people always talk about there being less oxygen on the top of Mount Everest, and that's really due to the decreased air pressure. Atmospheric pressure decreases because there is less air above you. At sea level, it's worth learning this, atmospheric pressure is approximately 100,000 pascals. What about pressure under the ocean? If you've been scuba diving, you'll be aware of this. Well, the pressure massively increases the lower down you go. So pressure increases as depth increases. And really, that's just because you've got so much more water above you. And there's an equation which really explains this, which states that pressure difference equals height times density times gravitational field strength. So obviously, as we get lower in the ocean, that height value increases and therefore the pressure increases. Do be prepared to always point out that pressure at a point in a gas or liquid acts in all directions. It's worth including that statement in your answers. Let's do another calculation. The depth of a liquid in a glass is 22 centimeters. The density of the liquid is 1080. Calculate the pressure difference at the bottom of the glass due to the liquid. Give your answer to 2 significant figures. So pressure difference equals height times density times gravitational field strength. Let's convert our 22 centimeters to meters, so that's 0.22 meters. Our density is 1080, gravity is 10, so our final answer is 2,376 pascals. The photograph shows a small glass ball used to investigate density and pressure. The mass of the ball is 19 grams, the density is this. State the formula linking density, mass and volume. Density equals mass over volume. Calculate the volume of the ball. So I know the density is 2.3. The mass we were told is 19. I'm after volume. So I do 19 divided by 2.3, which is 8.3. The ball is dropped into deep water and sinks to a depth of 560 centimeters. State the formula linking pressure difference, height, density, and gravitational field strength. So pressure difference is height times density times gravitational field strength. Calculate the increase in pressure at this depth. Just be careful with your units. Because our density is given in meters cubed, I want my height in meters, so that's 5.6. My density is given here, it's 1,000. Gravity, remember, is 10. So we get an answer of 56,000 pascals. So I want to go through the change of state topic, and honestly the best thing to do is show you lots of past paper questions. I'll quickly show you a few pages from my revision guide though in terms of content. So when you heat a system, clearly you increase the kinetic energy of the particles. And what that does is that it increases the energy stored within the system. Temperature is related very strongly to the kinetic energy of the molecules. So when you increase the kinetic energy, it will cause the temperature to increase and it can produce a change of state. So I'm sure you're very familiar with these changes of state, but obviously if a solid turns into a liquid, like an ice cube turns back into liquid water, we call that melting. If a liquid turns into a gas, it's either boiling or evaporating. When a gas turns into a liquid, such as when you have a shower and then the steam hits the cold window, you'll see condensation, so that's condensing. And then liquid to solid is freezing. In chemistry, you'll have also met sublimation, which is when a solid turns directly into a gas, such as the case of iodine. If they're being kind to you, they'll ask you about the structure of solids, liquids and gases. Be prepared to talk about the arrangement of particles. So obviously with the solid, you have a regular arrangement of particles. You've got strong forces holding those particles together, and the particles vibrate around in fixed positions. They have little kinetic energy. Liquid, you'll find that the particles can move over each other slowly. They're more irregularly arranged compared with the solid, and there's intermediate forces holding those particles together. The gas particles have lots of kinetic energy. They've got very weak forces holding them together, and you'll find that they move in a rapid random motion. Let's look closely at a graph showing changes of state. Be prepared to recreate this kind of graph. The thing to be aware of is when a substance is changing state, it remains at the same temperature. So when our solid is turning into a liquid, i.e. the ice is melting, look, it remains at 0 degrees Celsius. When our liquid is turning into a gas, i.e. it's boiling, look, that occurs at 100 degrees and it occurs at the same temperature. So a change in state needs to be shown on your graph as a horizontal line, and that's the main take-home message when you see these sorts of graphs. Now, the specific heat capacity is the energy required to increase the temperature of 1 kilogram of a substance by 1 degree Celsius. Again, you might have met this equation in chemistry, which states that change in thermal energy is mass times specific heat capacity times the temperature change. Just be careful with that mass. That's the mass of your liquid. Specific heat capacity is a particular number. They'll give you that in the question most likely. And then here's your change in temperature. So just to put that into practice, we've been told that we've got a substance with a mass of 1.2 kilograms. We're being asked to calculate the energy required to raise the temperature of the substance from 10 degrees Celsius to 37 degrees Celsius. And here's its specific heat capacity. So write your equation. The mass we know is 1.2. The specific heat capacity we were told is 840 in the question. What is our temperature change? Well, it's the difference between those two numbers. And here's our final answer. The table shows some data about the dog and the water in the bag. The dog sits on the bag for 22 minutes. Calculate the energy transferred from the dog to the water by heating in 22 minutes. Look down at all the information you have here. We want to use EPT. So that's energy equals power times time. Power is in the correct unit already, so we don't need to touch that. Be careful with your time unit. It's in minutes, so we need to multiply that by 60 to get it into seconds, to get a final answer of 99,000 joules. State an assumption you have made when calculating the energy transferred. You've got lots of options here. I'm just going to point out that we're assuming that the dog doesn't change temperature. Calculate the temperature of the water after 22 minutes. It's worth 4 marks. So I'm going to use Q equals MC delta T. We've calculated the energy transferred. It was 99,000. What is our mass? It's 8.7 kg. C is our specific heat capacity, which we're told is 4,200. I'm after the temperature change, so that's my X. Simplify the right-hand side. So do 8.7 multiplied by 4,200. Divide both sides by 36,540 to get 2.71 degrees Celsius. Just check what's going on. So the dog is going to actually cause that water to heat up. So we need to take that initial temperature and then add the 2.71 we've just calculated. This is a question about a melting ice cube. The diagram shows an ice cube placed on the ground. The mass of the ice cube is 3.7 grams, and its area of contact with the ground is this. Calculate the pressure the ice cube exerts on the ground. Check your units. It's the standard unit of pressure, pascals, which means we need our mass in its standard unit of kg. So we work that out by dividing that number by 1,000. Here's our formula triangle, so we can see that pressure equals force over area. Be careful, we don't have a force value yet because this is a mass. So you're going to need to use this equation here to calculate your force. Remember that weight and force are the same thing. So we're going to do 3.7 over 1,000 times by gravitational force on Earth, which you need to remember is 10. So we've calculated our weight and therefore our force. The area was 2.6 times 10 to the minus 4 meters squared. So our answer is 142 pascals. The ice cube melts and becomes a puddle with a larger cross-sectional area. Explain how the pressure of the ice cube on the ground changes when it melts. So if pressure equals force over area, force stays the same because it's the weight of the ice cube, but the area increases. So if you're dividing the same number by a larger number, it means that pressure value must decrease. Ice melts at a temperature of 0 degrees Celsius. On the axis, sketch how the temperature of the ice cube changes as it rises from a temperature of -10 to a temperature of 20 degrees Celsius. So remember, as that ice cube changes state, it stays at constant temperature, which we'll see as a horizontal portion on the graph. So we'll do this. We go from -10, we know it melts at 0 degrees. So here it is melting, and then it's going to achieve a temperature of around 20 degrees, so we need to draw it like this. Explain the changes that occur when a solid melts. Refer to particles in your answer. You want to say that bonds between particles are broken. Particles go from regular to irregularly packed. Ideal gas molecules. One thing they regularly ask you to do is to explain how pressure is created by a gas in a container. It's worth learning this as a perfect answer. So what happens is the gas molecules have random rapid motion and collide with the walls of the container, creating a force. Remember, in physics, it's always worth stating an appropriate equation. The appropriate equation here is that pressure equals force over area. What happens if you increase the temperature? You just need to say here the same sort of thing. Just say that the gas molecules have greater kinetic energy. They're still going to be moving with a random rapid motion, but they're going to collide with the walls with a greater force. So don't feel like you have to learn these notes twice. Just learn the original answer and then add a few extra words. Clearly there's a relationship between temperature and kinetic energy. So as temperature increases, as we just said, the kinetic energy of the gas molecules also increases. But that works the opposite way, which is if we reduce our temperature, and so you get to a point where the kinetic energy of the gas is so reduced, you end up with a pressure of a gas which is actually 0, and this happens at a very specific temperature, which is -273 degrees Celsius. You need to learn that number, which is the same as 0 Kelvin. So you'll be very familiar with degrees Celsius. At this point in the specification, you also need to be aware of a second temperature unit, which is Kelvin, and this is known as absolute 0, the coldest temperature possible. Here's our relationship, our directly proportional relationship between kinetic energy and temperature in Kelvin. It goes through the origin. As you reduce your temperature, the kinetic energy also reduces. Let's look at how we convert between our temperature units. If you want to go from Kelvin to degrees Celsius, you need to minus 273. If you want to go from degrees Celsius to Kelvin, you need to add 273. So in this example, we're being asked to convert room temperature, which is 20 degrees Celsius, to Kelvin. What do we have to do? We need to add 273 to get an answer of 293 Kelvin. Let's take a second example. Convert 20 Kelvin to degrees Celsius. What do we need to do? We need to minus 273. Let's look at some various gas law equations now. First one I want to show you looks like this. It states that P1 over T1 equals P2 over T2. So you'll be given information relating to three of these values: pressure 1, pressure 2, temperature 1 and temperature 2. Be careful, to use this equation correctly, the temperature must be in Kelvin. So you might need to do some converting in order to sort out your units. Let's put it into practice. So the pressure of the gas is 106 kPa when the temperature is 30 degrees Celsius. The gas is heated to 320 degrees Celsius. Calculate the pressure of the gas when its temperature is 320 degrees Celsius. Assume the gas has constant volume. So let's label all our numbers. That's P1, T1. It's our second temperature, and we're being asked to find the second pressure. However, in order to use this equation here, P1 over T1 equals P2 over T2, remember we need Kelvin. So let's get converting. What is 30 degrees Celsius in Kelvin? Well, we need to add 273. What is our second temperature in Kelvin? Again, we need to add 273. Now we're ready to use this equation. So do 106 divided by 303 and then multiply by 593 to get a final answer of 207 kilopascals. A second gas law is Boyle's law. This states that P1V1 equals P2V2. The first pressure multiplied by the first volume equals the second pressure multiplied by the second volume. I think this is a slightly more straightforward equation to use. Let's work our way through this example. The air inside a sealed container is the atmospheric pressure. So that's your P1. The volume of the container increases from 105 to 130 centimeters cubed. That's V1, V2. Calculate the pressure inside the container after the volume has been increased. Sub in your values really carefully. Do 101 times 105 and then divide your final answer by 130 to get a P2 value of 82 kilopascals. Scientific balloons are tested in a laboratory before they are used. In the first test, the pressure of the air inside the balloon is 100 kPa. The balloon is sealed and has a volume of 92 meters cubed. The pressure of the air inside the balloon is reduced to 64 kPa by reducing the external air pressure. Calculate the new volume of the balloon. This is why I say it's so important to label all your numbers, because it helps you see straight away that the equation you need here is P1V1 equals P2V2. Sub in all your numbers in the right places. You don't need to touch the units, because look at the answer unit. To find V2, divide both sides by 64 to get to 2 sig fig 170 meters cubed. Give an assumption that is made in the calculation that we have a constant temperature, because remember that will affect the volume of the gas. The pressure of the air in the balloon is returned to 120 kPa. The temperature of the air inside the balloon is 290 Kelvin. The balloon is tested again, changing the temperature of the air and keeping the volume of the balloon constant. Explain why the pressure of the air in the balloon decreases when the temperature of the air decreases. So let's talk about what's happening. When the temperature decreases, the particles or gas molecules have less kinetic energy, so collide with the walls of the balloon less frequently and with less force. Remember that pressure equals force over area, so if you reduce your force value, then your pressure decreases. Calculate the temperature of the air when the pressure of the air in the balloon is 64 kPa. Give your answer in Kelvin. There's P1, this is P2, we're after T2, and this is T1. Just make sure you read all the wording in the question so you know how I'm arriving at that. So remember, we need P1 over T1 equals P2 over T2. P1 is 120, T1 is 290, P2 is 64, and we're after T2. This equation relies on us having our temperatures in Kelvin, so it's handy that we don't need to touch it. Sort out the left-hand side by doing 120 divided by 290. Then cross multiply, so we do 64 divided by 0.4137 to get 155 to 3 sig fig. Magnetism and electromagnetism. So starting with which metals may become magnetized, we're talking about iron, steel, which is an alloy of iron, nickel and cobalt. Now, iron is what's known as a soft magnetic material, and that's because it loses and gains magnetism easily. Steel is known as a hard magnetic material because it retains its magnetism. So if you're after a permanent magnet, you would choose to make it out of steel as opposed to iron. Thinking about a simple red and blue magnet, it has a north and south pole. Remember that opposite poles attract, so a north pole will attract a south pole. Like poles will repel, so two south poles will repel, two north poles will repel. Now, a magnetic field line is the space around a magnet where magnetism can be detected. And again, taking our bar magnet, if we consider the direction the magnetic field lines run, they always run from north to south. Make sure you can label that on a diagram. And how do we know that? Well, there's two simple experiments we can carry out, one involving plotting compasses and the other one involving iron filings. So if they ask you to describe an experiment demonstrating magnetic field lines around a bar magnet, you can start by saying that you want to sprinkle iron filings on a piece of paper, place your bar magnet below the paper, tap the paper, and the iron filings will arrange themselves in the shape of the magnetic field lines around a bar magnet. If you use the plotting compass approach, you want to place the plotting compass close to the magnet on a piece of paper and then use your pencil to just show the direction that the plotting compass is pointing in, and then just keep moving your plotting compass to a new position, marking the new direction, and then join together all those points to get the shape of the magnetic field lines around a bar magnet. Now, where are the magnetic field lines strongest? Closest to the poles of the magnet, and we'll be able to see that visually because the magnetic field lines will be closest together. The magnetic field strength decreases the further away from the bar magnet, and we'll see that displayed as the magnetic field lines moving further apart. So how can we induce an object to become magnetized? We'll get your magnetic materials such as iron, place it in a magnetic field, and the object becomes a magnet. Also, it only remains magnetized though whilst it remains within the magnetic field lines of the permanent magnet. One other thing they frequently ask you is to either draw a uniform magnetic field line or to describe a uniform magnetic field. So you'll see here that the magnetic field lines run north to south. The magnetic field lines are evenly spaced, and they are also parallel. Do draw a minimum of 4 magnetic field lines when asked to draw a uniform magnetic field. Electromagnetism now. So how do we create a simple electromagnet? You want to pass a current through a wire, wrap that wire into a coil, and then add a soft iron core. The coil of wire we sometimes describe as being a solenoid. How can we make the strength of that electromagnet stronger? Well, we can increase the size of the current. We can add more turns, which effectively means more coils of wire. Now we're going to talk about the motor effect, which is all about causing a coil of wire to move. So we need a coil of wire, we need permanent magnets. The coil of wire does need to be carrying a current. So why does the coil of wire move? Be prepared to describe this. So what you want to say is that the coil of wire carrying a current experiences a temporary magnetic field. This temporary magnetic field interacts with the permanent magnetic field of the bar magnets, creating a force which moves the wire. And you might actually have tried this out if you're at school. A similar thing happens with a charged particle. So if we think of a charged particle as carrying a current, that current produces magnetic fields. The magnetic field of the charged particle interacts with the permanent magnetic field of the bar magnets, creating a force which moves the charged particle. But going back to our more generic motor effect, so we've got a coil of wire which we know is moving due to the interaction of the temporary magnetic field of the coil of wire and the permanent magnetic field. It's creating a force which turns our coil of wire. How can we increase the strength of the force? By increasing the current, increasing the number of turns, increasing the strength of the magnetic field. As part of a simple motor, you might see some carbon brushes which provide contact, as well as a split ring commutator which switches the direction of the current every half turn. This helps to keep the coil of wire spinning continuously. They love asking you to determine the direction of force on a wire, and you need to use Fleming's left-hand rule to do that. It's a way of working out the direction of the force by knowing the direction of the current and the magnetic field. So the first thing you need to know is that the thumb represents the direction of the force. Your first finger represents the direction of the magnetic field. Remember, that always needs to run from north to south. Your second finger represents the direction of the current. So commonly in a question, you'll be told the direction of the current. You need to remember that the magnetic field always runs north to south. As long as you hold your fingers so that they are at 90 degrees to each other, by lining up your magnetic field and the direction of your current correctly, that will then tell you the direction of the force. It could be upside down, it could be pointing up, it could be left, it could be right. So do make sure you fully understand Fleming's left-hand rule and how that can help you predict the direction of a force. Now, a loudspeaker is just a fancy way of describing the motor effect in greater detail. A loudspeaker is used to amplify sound waves. So how can we use electromagnetism to describe how a loudspeaker works? Well, begin with your usual motor effect answer. So the wire carrying a current experiences a temporary magnetic field. This temporary magnetic field interacts with the permanent magnetic field of the bar magnets, creating a force which moves the speaker cone. The speaker cone vibrates the air molecules, creating sound waves which reach our ear. You'll find that an alternating current is supplied to our speaker cone, and that's because the alternating current, remember from the electricity topic, is a current which continuously changes direction. So because you're changing the direction that your second finger is pointing in, clearly that's going to change the direction of your thumb and therefore the force on the speaker cone. We now need to look at electromagnetic induction, which we call the generator effect. So it's really how we're using magnets to produce a voltage and therefore a current. It's a very similar setup to the motor. The way to easily distinguish between whether you're looking at the motor or looking at the generator is what is included. In the motor, you need to have an input of current, which is why you'll see a power supply or a cell. With the generator, you'll need a way of detecting that there's current or voltage, such as an ammeter, a voltmeter, a galvanometer, or even a light bulb which illuminates when the current is flowing. So with Fleming's left-hand rule, we discussed how if we input a magnetic field and a current, we get a force. If we take Fleming's right-hand rule, the fingers remain the same. So your thumb is still your motion, your first finger is your magnetic field, your second finger is your current, but this time you're inputting both a force, motion, as well as your magnetic field. So your output will be, in effect, current. And that is the whole point of the generator. So how do we get the output of a current? The simplest way to do this is to push a magnet through a coil of wire connected to a complete circuit. What happens is the magnetic field lines get cut by the coil of wire, which induces a voltage, and this is what we call electromagnetic induction. If this is part of a complete circuit, then current is also induced. The faster that those magnetic field lines are cut by the coils, the greater the voltage induced. So you could move your magnet faster, or you could have more turns of wire. You could also use stronger magnets to increase the size of the voltage produced. The region of space around a magnet is known as the magnetic field. Which of these diagrams correctly represents the magnetic field around a bar magnet? So we need arrows pointing from north to south. Just look down these super carefully. That's going from south to north, so it's not that one. North to south, yep, that's fine. The answer is B. The diagram shows two bar magnets placed close together. Which of these describes what happens to the two magnets? So we have a north pole facing a south pole, opposites attract. So the answer here again is B. Which of these magnet arrangements gives a uniform field between the poles? So we need them laid out so they're facing each other, running north to south. So we've got two like poles here which will repel. They're not facing each other. The answer here is C. You can see in D that the magnetic field lines wouldn't be running parallel to each other, and that's part of our definition of a uniform magnetic field. So if I were to draw it on this one, it would look like this, parallel magnetic field lines. State the name of a material that would be suitable for use as a permanent magnet. We need a hard magnetic material such as steel. A student investigates the magnetic fields produced by magnets. Describe a method he could use to determine the shape and direction of the magnetic field produced by a bar magnet. You may use a diagram to help your answer. So describe a method either involving iron filings or plotting compasses. I like the iron filings method personally. Sprinkle iron filings on top of paper. Place bar magnet beneath. Tap the paper, the filings arrange themselves in the pattern of the magnetic field lines. The diagram shows the shape of the magnetic field around the bar magnet. Add two arrows to the diagram to show the direction of the magnetic field, so it always runs from north to south. Explain how the diagram shows that the strength of the magnetic field changes. It's all to do with how close together the magnetic field lines are. The field is strongest where the lines are closest together, so close to the poles. The diagram shows part of the electric motor inside the fan. Explain why the coil starts to rotate when there is a current in the coil. It's your kind of perfect motor effect answer. So you're going to say the coil carrying a current experiences a temporary magnetic field which interacts with the permanent magnetic field. This creates a force which moves the coil. Which side of the coil moves vertically upwards? So we need to use Fleming's left-hand rule. Remember, your thumb represents the force. Your first finger is the magnetic field direction, which is always north to south. And your second finger should represent the direction of the current. So we need to line up our left hand with the various thumb and fingers so that the force, your thumb is pointing up. So there's your magnetic field running north to south. So there's your first finger. If I look at this side of the coil, there's my current direction, which is actually pointing towards me. And actually what I find is that my thumb is pointing upwards, meaning that that side of the coil is moving upwards. So I know that it's YZ. Transformers. There are two types of transformer, a step-up transformer and a step-down transformer. And the role of a transformer is to alter the output voltage. As the name suggests, with a step-up transformer, you'll be increasing the output voltage. With a step-down transformer, you'll be decreasing the output voltage. We'll first of all describe why we need transformers, and then we'll look at their construction in great detail. So where you have electricity generation, such as a fossil fuel power station, you will have a generator. You'll also have a step-up transformer, and a step-up transformer increases the output voltage. But why do we want to increase the output voltage to something like 500,000 volts? Well, that's because of the equation P equals IV. Power equals current times voltage. You must remember that power will remain constant If we increase the voltage, it automatically therefore means that the current must be decreased. This is a good thing because after all, high currents have a strong heating effect. This is why you often need a thick wire if the circuit uses a large current. And that heating effect means the energy is wasted, it is dissipated to the surroundings. So the real purpose of a step-up transformer at a power station is to reduce energy losses. Clearly, however, we don't want 500,000 volts entering our home. That would be incredibly dangerous. So at our homes, you find a step-down transformer. This will reduce the voltage to a safe level, around 230 volts, which can be used in our homes without risk. What about the construction now of a step-up and step-down transformer? Well, both consist of a laminated soft iron core. With a step-up transformer, you'll find that there are more turns on the right-hand side of the coil, which we refer to as the secondary coil. With a step-down transformer, you'll find that there are fewer turns on the secondary coil compared with the primary coil. Just have a look at these diagrams and you'll see that this is true. So how does a transformer work to alter the output voltage? Well, first of all, you need to supply an alternating current to your transformer. Remember, an alternating current continuously changes direction. Because you're supplying an alternating current, it means that you're going to be producing a magnetic field in the primary coil. And because that current is alternating, the magnetic field will also be changing in the core. The purpose of the soft iron core is to strengthen the size of the magnetic field. And obviously, because all parts of the iron core are touching, the secondary coil will also experience a changing magnetic field. That changing magnetic field will be cut by the coils of wire on the secondary coil, so the right-hand side, so clearly a voltage will be induced. And the size of the voltage will totally depend on how many turns we have. The greater the turns, the greater the size of the voltage, which is why a step-up transformer has more turns on the secondary coil as opposed to the primary coil. So the first equation you need to be aware of is that the primary voltage divided by the secondary voltage equals the number of turns on the primary coil divided by the number of turns on the secondary coil. Let's put that into practice using this question here. A step-down transformer has 160 turns on the primary coil and 45 turns on the secondary coil. The input voltage is 12 volts. Calculate the output voltage. So always state your equation. Make sure you put all your numbers in the right place. And then do 12 divided by 3.5 to get an output voltage of 3.4 volts. A second equation now, which states the input power equals output power. Remember from the electricity topic that power equals current times voltage. So voltage on the primary coil times current on the primary coil equals voltage on the secondary coil times current on the secondary coil. Bear in mind we're assuming that there's no energy loss. So let's attempt a question using this equation. A step-up transformer has an input voltage of 230 volts and an output voltage of 270 kV. The transformer has an input current of 90 amps. Calculate the output current. State our equation. Put everything in the right place. Be careful with your output voltage. You need to convert that to volts by timesing by 1,000. Do 230 times 90. Divide both sides by 270,000 to get an output current of 0.077 amps. A student investigates transformers. The diagram shows a typical transformer. State the name given to this type of transformer. The way you work that out is by considering the number of turns on the primary versus secondary coil. Because there are fewer turns on the secondary coil, we say it's a step-down transformer. The student investigates the effect of changing the number of turns in the secondary coil. This is his method. Apply a constant maximum voltage to a primary coil with 1,200 turns. Use a secondary coil with 100 turns. Measure the output voltage on the transformer. Replace the secondary coil with one with 200 turns and measure the output voltage again. The student repeats this method using different numbers of turns in the secondary coil. Suggests how the student could improve the reliability of his investigation. Reliability is all about your ability to repeat the experiment and discard any anomalous results. These are the students' results. Draw a table of these results. Let's go number of turns, because after all that's what we're changing, that's our independent variable. And then on the right hand column what we're measuring, so that will be the output voltage. Our dependent variable, include units, and then complete your table. Remember, units should never appear in the main body of the table, they should always appear in the table heading. Suggest how the student can improve the precision of his voltage measurement by increasing the sensitivity of the voltmeter. The student plots this graph to show the results of his investigation. The student plots one of his results incorrectly. Draw a circle around the incorrectly plotted result on the graph. As I look at the pattern, I can see it's this one here. Draw a line of best fit, so we're going to discard that anomalous result and just stick with the others. Describe the relationship shown by the graph, so say what you see. You can see here that as the number of turns increases, the output voltage increases, and we can see, because it's a straight line, that it's a linear relationship. You can say it's directly proportional as long as it passes through the origin. If your line doesn't pass through the origin, you can't say that it's directly proportional. The primary coil has 1,200 turns. Using the student's data, calculate the primary voltage used in his investigation. So we're using this equation, voltage primary over voltage secondary is number of turns primary over number of turns secondary. We know that the primary coil has 1,200 turns. We're being asked to find the primary voltage. We're going to use the student's data to pull out the missing info here. Doesn't matter which point you use. I'm going to go in here with 400 turns on the secondary coil, giving me an output voltage of 5. Multiply both sides by 5 to get a final answer of 15. Radioactivity. We need to start by looking at the structure of an atom. So there's a huge overlap here with chemistry. So remember, your atom is made up of a nucleus, which contains protons and neutrons, and then surrounding the nucleus are shells containing electrons. Now the mass of a proton is 1, the mass of a neutron is 1, and the mass of an electron is extremely small. It's approximately 1 divided by 2,000. So when we think about the mass of an atom, it's largely found in the nucleus of the atom, and indeed to find the mass you need to add the proton number to the neutron number. You'll be able to find this value in the periodic table. It is the top number. So for example, the mass number of oxygen is 16 because it comprises of 8 protons and 8 neutrons. In terms of their relative charges, electrons have a charge of -1, protons have a charge of +1, and neutrons are neutral as their name suggests. So why does an atom not have an overall charge? Because it has an equal number of protons and electrons. Now elements in the periodic table are arranged in order of relative atomic number. This is the same as the proton number. So it's important that you're aware as soon as the proton number changes, you have a new element. To find the number of neutrons, you need to do the mass number, take away the proton number. So if you have a look at sodium, it has a mass number of 23, a proton number of 11, which means you can calculate that its neutron number is 12. Do make sure you're happy to do this. Now the definition of an isotope is atoms of the same element with the same number of protons but a different number of neutrons. This means that you'll have some radioactive isotopes which have excess number of neutrons. This makes them unstable and likely to decay and give off radioactivity, which is where the title of this topic comes from. The type of radiation which may be emitted includes alpha, beta and gamma, and we need to talk about each of these in turn in great detail slightly later on. Let's take 2 isotopes of carbon, carbon-12 and carbon-14. Carbon-14 is radioactive because it contains 2 extra neutrons. Because both isotopes are carbon, they must have the same proton number, which if you check the periodic table is 6. So what are the 3 types of radiation? Well, we just said that they were alpha, beta and gamma. So what is an alpha particle? Well, it consists of 2 protons and 2 neutrons. Do be prepared to say that. and as such it has quite a high mass of 4, because remember each proton and each neutron has a mass of 1. It's quite highly charged as well, owing to those 2 protons. It has a 2+ charge. When an atom undergoes radioactive decay and the nucleus gives off an alpha particle, you will need to calculate the new mass number and the new atomic number, which is why it's so important that you understand how the proton and neutron number are related. So taking uranium-230, it has an atomic number of 92. If it loses an alpha particle, it's going to lose 2 protons, which will reduce the atomic number to 90, meaning that you have a new element. Use your periodic table to identify the element, and you'll see that it's thorium. Because the alpha particle contains 2 protons and 2 neutrons, that means that the mass number of the new element will be 4 less than the original uranium. As such, thorium has a mass number of 226, and you do need to acknowledge the loss of the alpha particle by showing that on the right-hand side of the equation. Now, beta particles are fast-moving electrons. This means they have a much lower mass number compared with an alpha particle. After all, an electron has a mass of 1/2000. They're also less highly charged because the single electron has a charge of -1. So when an element decays and gives off beta radiation, what actually happens here is that a neutron turns into a proton and stays within the atom, whilst also giving off an electron, our beta particle. So let's consider what happens to the original element. Well, because a neutron has turned into a proton, they both have a mass of 1, which actually means that the mass number is unchanged. So if we take the carbon example, carbon-14, the element that is produced will still have a mass number of 14. But will that element still be carbon, or will it be another element? Well, let's understand what's happened to the proton number. Because a neutron has turned into a proton, in effect, the element has an extra proton. This means that it's a new element because it has a new atomic number. And actually use your periodic table and you'll be able to identify that that element is nitrogen. Do also show the release of the beta particle. You can show it as an electron or as a beta sign. Now, gamma is the most straightforward type of radioactive decay. Gamma you'll have met in the wave section of the specification. Gamma is an electromagnetic wave. So when an atom gives off gamma radiation, there'll be no change to either the atomic number or the mass number. Do remember that the atomic number is the same as the proton number. The mass number is the same as the total number of protons and neutrons. The nucleon number refers to the number of particles found within the nucleus of the atom. So strictly speaking, we're looking at protons and neutrons. So it's worth learning that the nucleon number is the same as the mass number. One thing they like to ask you to do is distinguish between the ionizing and penetrating powers of alpha, beta, and gamma. So alpha is the most ionizing, beta has an intermediate ionizing power, and gamma is the least ionizing. Remember that an ion is a charged particle that has either lost or gained electrons. A negative ion has gained electrons, a positive ion has lost electrons. In terms of their penetrating powers, this is reversed. Alpha is the least penetrating, gamma is the most penetrating. So we can consider their penetrating powers by looking at their range in air. Alpha can only travel a few centimeters, beta can travel around 50 centimeters, and we say that gamma has an infinite range in air. It will basically just keep going. But what can we use to stop alpha, beta, and gamma? Again, this links with their penetrating powers. Well, alpha is just stopped by paper, beta is stopped by aluminium foil, and if you want to stop gamma radiation leaking out, you need to use meters thick concrete or several inches of lead sheeting. How can we detect radiation using a Geiger-Müller detector? One unit of radiation is the becquerel, BQ. Now, background radiation is radiation which is always present in our atmosphere. Background radiation comes from a large number of places, including radon gas, cosmic rays, X-rays used in medicine, foods such as bananas, and nuclear waste. If you're trying to measure the amount of radiation being given off a radioactive source, it is important that you use your Geiger-Müller detector to measure the level of radiation with the source present, and also to measure the level of radiation when the source is absent, because that will give you an indication of the background radiation which needs deducting from your final value. Let's look at some uses of various radiation. So alpha radiation can actually be used in smoke alarms. So within a smoke alarm found in your home, you'll have an alpha source, and then there'll be a detector just a few centimeters away, which makes sense because remember, alpha has a very low penetrating power. So when there's no fire in your home, that alpha source is constantly being detected. However, what happens when there's a fire in your home is the smoke gets in the way, and the smoke readily absorbs the alpha particles, meaning that they can no longer reach the detector, and therefore the fire alarm sounds. Beta is used to control the thickness of aluminium foil that you use to wrap your sandwiches in. You'll have a beta source and then a detector on the other side of the aluminium foil. If that reading reduces on the detector, it means that the aluminium foil is too thick because the beta particles aren't getting through. So that means that rollers will squeeze together to make your aluminium foil the right thickness. We can use radioactive isotopes in medical tracers. That really means looking at the functioning of particular organs such as the kidney. So someone might be given a drink containing radioactive iodine, which gives off gamma. Now that's good because remember, gamma is the least ionizing of the three types of radiation, and ionizing radiation is really dangerous because it causes cell mutation, which can lead to cancer. So if you're going to be swallowing one of these sources, you want it to be the least ionizing one, so in this case gamma. The other good thing about gamma is because it is so penetrating, it can be detected outside of the body, enabling you to look at the functioning of the kidney. It's also important that you pick a source which has quite a short half-life because you don't want it to stay active within the person's body. So one with a half-life of around 7 hours would be appropriate. We can use radioactive carbon to date various plants and animal fossils. And how does that work? Well, if you think about a tree, while it's alive, it's absorbing carbon dioxide so that it can photosynthesize and produce glucose. So that carbon becomes part of the tree, and over its lifetime it will be taking on both carbon-12 and radioactive carbon-14. Now when the tree dies, obviously it's not photosynthesizing anymore, so it can no longer take on either carbon-12 or carbon-14. As the carbon-14 decays, it becomes less radioactive, and as a result its radioactivity decreases. So by comparing a tree that's alive today with your fossil and looking at its radioactive levels, you can work out its age. As we've already said, ionizing radiation is dangerous, so how can we limit our risk? Well, obviously we can limit our exposure time. We can monitor how much radiation we've been exposed to using photographic film. We can use lead aprons, handle radioactive sources with tongs, and in general just be very mindful. Now, nuclear power stations produce an awful lot of radioactive waste. It's really important that this waste gets properly handled because if it's allowed to leak into surrounding water sources, it can get into people's drinking water, it could cause cancer. So it's important when these radioactive isotopes have such long half-lives, sometimes thousands of years, it's important that all the waste is stored in rust-proof plastic containers and that it's kept very securely to avoid any risks from people using it as a weapon. If they're being really annoying, they'll ask you the difference between irradiation and contamination. So contamination is when the radioactive source is on the object, it is contaminating your object. Irradiation, as the name suggests, is when your object is exposed to a source of radiation. With contamination, because your object is contaminated, clearly you can't block the radiation using lead shielding. However, because irradiation is all about an object being exposed to a source of radiation, you can place lead shielding between the object and the radiation and therefore block the radiation. With contamination, the object is radioactive as long as the source is on the object, whereas with irradiation, it doesn't cause the object to become radioactive, and the radiation stops as soon as the radioactive source is removed, whereas with contamination, radiation remains as long as the source is on it. Let's do a quick run through of half-life. So half-life is the time taken for half the radioactive nuclei to decay. Remember, because of those excess neutrons, they're likely to give off radiation, and when they do that, we say that the nuclei has decayed. So if you look at a very typical half-life graph, here we're choosing to talk about radioactivity as a percentage as opposed to counts per minute or becquerels, doesn't really make a difference. The graph will still look very similar. If you look on your x-axis, that's time. So at the start, that's when you've got your largest sample of radioactive nuclei. And then obviously, as those nuclei start to decay, the activity of the sample decreases quickly at the start, and then it slows down and reaches this asymptote here. If they ask us for the time for the half-life of this particular sample, you just read across at 50%, read down on the x-axis, and you can see that the half-life for this sample is 10 years. It took 10 years for half the radioactive nuclei to decay. And as we've written here in the guide, it's a random process and it's different for different radioactive isotopes. If you're at school, you might have done a coin toss experiment where you pick 100 coins, you toss the coins, every time they land on a head, you say that they've decayed and you remove them from the sample. Then you toss the remaining coins, every time they land on a head, you remove. Keep track of those numbers, plot them on a graph, and you'll see a very similar relationship. This is a good model aside from the fact that there's only a very set number of times that you'd be willing to do it for, whereas in reality we're talking about millions of nuclei. But largely speaking, this topic relates to half-life calculations. So I'll run you through some examples now. Iodine-129 is an isotope found in radioactive waste from nuclear power stations. Iodine-129 has a half-life of 15 million years. A sample of iodine-129 has an activity of 72 kBq. What is the activity of the sample after 60 million years? So do read the wording really carefully, because there's no hard and fast way of doing this, and you do need to make sure you're doing the correct calculation. So the first thing you want to do is work out how many half-lives could have taken place in 60 million years. So if one half-life takes 15 million years, then there's time for 4 half-lives to have occurred. So in effect, we take our 72 kBq, which was our original activity, and we halve it 4 times. This does take a little bit of practice, but you will get your head around it. So the first half-life will take that down to 36 kBq. The second one will take it down to 18 kBq. The third takes it to 9. And the fourth takes it to 4.5. So what will the activity of the sample be after 60 million years? Your final answer is 4.5 kBq. Let's do another half-life calculation now. So sodium-24 has a half-life of 15 hours. If a sample of sodium-24 has an original activity of 500 BQ, what will its activity be after 60 hours? So we have a time frame of 60 hours. We know that one half-life took 15 hours, which means 4 half-lives have occurred. The original activity was 500 becquerels, so after 4 half-lives we'll be down to 250, 1 to 5, 62.5, 31.25 becquerels. So our final answer is that after 60 hours, the original activity of the sodium-24 will have reduced to 31.25 becquerels. After 42 days, the activity of a sample of phosphorus-32 has decreased from 400 becquerels to 50. What is the half-life? So you've got slightly different wording here. Work out how many half-lives have occurred. So one half-life takes you to 200. 2 half-lives take you to 100. And 3 half-lives take you to 50. So write that out, 3 half-lives occurred. So in 42 days, 3 half-lives occurred. So how long did it take for one of those half-lives to take place? 14 days. So your answer is the half-life of phosphorus-32 is 14 days. Lead-210 is a radioactive isotope of lead and is represented using this symbol. State what is meant by the term isotope. This is a definition which needs learning off by heart. Atoms of the same element with the same number of protons but a different number of neutrons. So if we look at the element symbol for lead, remember the top number is the mass number, which is the total of the protons and neutrons, and the bottom number is the atomic number, which is the same as the proton number. So how many protons are in the nucleus? It's this bottom number here, don't get distracted, it's 82. A sample of lead-210 has an initial activity of 240 becquerels. After 66 years, the activity of the sample is 30 becquerels. Calculate the half-life. So how many half-lives have taken place? So to go from 240, one half-life takes you to 120, two half-lives takes you to 60, three half-lives takes you to 30, which is where we need to get. So we know that 3 half-lives occurred in 66 years. So it makes sense that 1 half-life takes 22 years. Lead-210 decays into lead-206 through a number of stages. This involves 1 alpha decay and a number of beta decays. This incomplete equation summarizes these stages. Complete the equation by giving the missing numbers, write your answers in the spaces provided. With 1 alpha decay, that's going to decrease the mass number by 4. It's going to decrease the atomic number by 2. So there we are, showing that an alpha particle, after all, has a mass of 4 and an atomic number of 2. Just make sure the left and right hand sides of the equation add up. So we've got 210 on the left. 206 plus 4 is 210 with that 0, so that's okay. Over here, we've got 82. 82 plus 2 is 84, but we need it to equal 82, so we need 2 beta particles, as that will bring that number down there to minus 2. So it becomes 82 plus 2 is 84, minus 2 is 82. So everything adds up on the left and right side. Let's now talk about nuclear fission and nuclear fusion. So nuclear fission occurs within a nuclear reactor. It's how we get energy from nuclear power. So in order to do that, we need a fuel, and that will be a radioactive isotope such as uranium-235. Nuclear fusion, which I'll talk about in greater detail later on, is something which occurs naturally in stars. So do bear in mind, nuclear fission occurs in a nuclear reactor. Nuclear fusion occurs naturally in stars. So what happens in nuclear fission fundamentally is that a uranium nuclei absorbs a neutron. The nuclei splits to form 2 smaller daughter nuclei, and 2 to 3 neutrons are released, which are able to collide and be absorbed by other uranium nuclei. And so the process continues, and this is what we call a chain reaction. As I've already said, this occurs in nuclear reactors, and you do need to learn the different components of a nuclear reactor. So as I've already said, we need a fuel source. That will be contained within the fuel rod, and most likely it is uranium-235. Clearly a huge amount of radiation is going to be given off, and that's the purpose of the lead shielding, to prevent that radioactivity escaping. Now, in order to stop the chain reaction getting out of hand, you have control rods. The role of the control rods is to absorb excess neutrons. By removing neutrons, it means that there are fewer neutrons available to be absorbed by uranium nuclei, slowing down the reaction. The control rods are made out of the element boron. Another important component of the nuclear reactor is the moderator. The moderator is made out of carbon, and its purpose is to slow the neutrons. The reason for that is to actually increase the chance of a nuclear fission reaction occurring. If the neutrons are too fast, then nuclear fission is less likely to take place. There's also a coolant, which is made out of water. This removes excess energy from the reactor. Nuclear fission shouldn't be confused with nuclear fusion, which, as I've already said, occurs naturally in stars. Here, as the name suggests, 2 nuclei join in order to form a larger nuclei, and the mass before is larger than the mass afterwards. There is a loss of mass during nuclear fusion. Huge amounts of energy are released. Now, very high temperatures and pressures are needed for nuclear fusion to take place, hence why it takes place in stars. And that's because if you think about what's happening, the nuclei are positively charged because they contain protons. They have a natural propensity to repel. So high temperatures and high pressures provide the kinetic energy required to overcome the repulsion forces of the 2 positively charged nuclei. Some of the energy stored in the nuclei of atoms can be used to generate electricity. A nuclear fission power station generates electricity. State the role of the moderator in a nuclear fission power station. The moderator, remember, slows the neutrons to increase the probability of fission reactions occurring. Some of the daughter nuclei produced in nuclear fission are highly radioactive and emit high-energy neutrons when they decay. Explain which feature of a nuclear fission reactor reduces the risks from these high-energy neutrons. So we want to talk about the control rods absorb neutrons, lead shielding prevents radiation escaping. The daughter nuclei can cause contamination and irradiation. Describe the difference between contamination and irradiation. So contamination is when a non-radioactive object comes in contact with a radioactive material. Whereas irradiation is simply when radiation is present. Nuclear fusion is another process that could be used to generate electricity. Describe the process of nuclear fusion. It's worth 2 marks. So it's the creation of a large nucleus from small nuclei, and remember it involves a loss of mass and the release of energy. State where nuclear fusion occurs naturally. Remember we need stars for that. Generating electricity from nuclear fusion is very difficult as the conditions needed are hard to achieve and maintain. Explain the conditions required for nuclear fusion. So we know we need very high temperatures and pressures, but why is that? It's because, remember, the nuclei have a natural propensity to repel each other because they're both positively charged. So we need a high pressure in order to force the nuclei to collide. So high temperatures are needed to increase the kinetic energy of the nuclei. The astrophysics topic concerns space, and we're going to start by talking about some key definitions. So starting with the universe is a collection of billions of galaxies. But what is a galaxy? Well, it's a collection of billions of stars. Our galaxy is known as the Milky Way. Now, our place within the Milky Way galaxy is known as the solar system. It consists of our star, which is called the Sun, and many planets. So let's go through the order of the planets, starting closest to the Sun, and I'm going to use the mnemonic. My very easy method just speeds up naming in order to remember the order. So we'll go through the order of planets, starting closest to the Sun. My stands for Mercury, very is Venus, easy is Earth, method is Mars, just, Jupiter, speeds, Saturn, up, Uranus, naming, Neptune. Closest to the Sun, we have our rocky small mass planets, and then further away we have our gaseous giants. As well as the Sun and planets, you'll also find moons within our solar system. These are known as natural satellites. They orbit planets, and you'll also find asteroids and comets. Now, all these various astronomical objects are kept in place by the gravitational force, and the strength of the gravitational force depends on 2 things: the mass of the object and the distance between 2 objects. Make sure you talk about this in terms of the mass of the object as opposed to the size. They probably won't award you a mark in the exam if you talk about Jupiter being much larger. One tiny detail is that our weight varies depending on where we are. Why is our weight much less on our moon compared with on the Earth? And it's all due to the equation weight equals mass times gravitational field strength. Mass is measured in kilograms and is unchanged. However, the gravitational field strength is much weaker on the moon compared with on the Earth. So if you do mass times a lower gravitational field strength on the moon, you'll find that your weight is much less on the moon compared with the Earth. So the gravitational force keeps objects in place, and that includes the moons orbiting the planets orbiting the Sun, and the comets also orbiting the Sun. Just bear in mind the shape of the various orbits of these astronomical objects. Moons and planets have circular orbits, whereas comets have highly elliptical orbits. This means they orbit in a squashed oval shape. They travel fastest when they're closest to the Sun, and that's because the gravitational force is strongest here. Comets are made up of dust, gas and ice, and you'll find that their tails always point away from the sun. A satellite is an object which orbits a planet. We've already met a natural satellite, the moon. Artificial satellites are put into space by us. A couple of extra definitions comparing day, month and year length. So what dictates that a day on Earth is 24 hours? Because a day is the time it takes for the Earth to rotate once on its axis. Different planets will have different day lengths. A month is the time it takes for our moon to orbit the Earth. It takes approximately 30 days. And a year is the time it takes for the Earth to orbit the sun. Again, different planets will have different year lengths. There's an important equation for calculating orbital speed, so that's how fast a planet, for example, orbits the sun. The equation for this is 2 pi r over t. You'll be provided with this in the exam. Just remember that you're doing 2 times pi times the orbital radius divided by the time for one orbit. Do make sure that your units align. They like to change the units an awful lot with this type of calculation. Use the answer box to dictate what unit you should be using. Let's do an example orbital speed question. A planet completes an orbit of a star in 70 days. The radius of its orbit is 1.5 times 10 to the 11 meters. Calculate the orbital speed of the planet in meters per second. This is exactly what I was talking about in terms of difficult units. We want our answer in terms of meters per second, and look, we have a time frame of 70 days. So we will need to get that into seconds. How do we do that? First of all, times it by 24 to get it into hours, then multiply by 60 to get it into minutes, and then multiply by 60 again to get it into seconds. So here's the equation: V equals 2 pi r over t. Keep 2 pi where it is. The orbital radius we were told was 1.5 times 10 to the 11. That's in meters, so we don't need to touch it. Then divide it by the time period to 3 significant figures. Our answer is as follows: 156,000 meters per second. Stellar evolution now. Now stars aren't actually all the same colour. The fact that they're super far away from us means that they appear the same colour in the night sky. But what the colour of a star actually tells you is its surface temperature. So actually the really hot stars will be blue, the medium hot stars will be yellow, and actually the coolest stars, contrary to what you might think, are red. Annoyingly, there's a part of the specification which expects you to classify stars based on their temperature. There's quite a silly mnemonic, which is O, be a fine girl, kiss me. And that tells you that O is a classification of a star, which is a blue star. It's the hottest possible star. Then B, slightly less blue star, slightly cooler star. A, F, G, K, M is going to be your red star, and it's going to be the coolest star. You could be asked about the life cycle of a star. That means the various stages that a star goes through in its lifetime. There are 2 categories: the life cycle of a small mass star and the life cycle of a large mass star. Now, both stars start off as a nebula. This is a cloud of dust and gas which is pulled together by the gravitational force. The next stage is known as a protostar for both mass stars. Here the kinetic energy still of the atoms increases and the temperature also increases. The main sequence is what we can think of as being the adult portion of a star's life. Here the forces are balanced and nuclear fusion of hydrogen occurs. This is the nuclear fusion we were just recently talking about. Huge amounts of light and thermal energy are released. There are now differences between a large mass star and a small mass star's life cycle. So let's take the small mass star, such as our sun. So eventually the hydrogen fuel runs out. The star expands to form a red giant. Elements with a higher MR in the periodic table are formed by fusion. The next stage of the life cycle of a small mass star is the white dwarf stage. Nuclear fusion reactions stop. A strong gravitational force causes the star to contract. And the final stage of a small mass star is the black dwarf stage, where the star continues to cool and contract. Let's now consider a large mass star. So the steps of the nebula, protostar and main sequence remain the same. So the main sequence, as I've said, is the adult portion of the star's life, where nuclear fusion of hydrogen occurs, huge amounts of light and thermal energy are released. But instead of entering the red giant stage, it enters the red supergiant stage. Hydrogen fuel in the core runs out, the core contracts, the layer around the core heats up, nuclear fusion reactions restart, and the star expands hugely. After the red supergiant stage, we reach a supernova. This is a massive explosion which results in either a neutron star being produced or a black hole if the star is a very, very large mass. Black holes have the strongest gravitational force. Nothing can escape, not even light. What does the brightness of a star depend upon? Well, it's three things. First of all, the distance of the star from the Earth. Secondly, the type of nuclear reactions taking place. And thirdly, what the star is actually made from. It's not enough to just look at the night sky and go, you know what, that star over there is the brightest. Because as we've already said, that hugely depends upon the distance of the star from the Earth. So we use a term called absolute magnitude to make this judgment of star brightness a lot fairer. So if they ask you for the definition of absolute magnitude, it's a measure of the brightness of a star at a standard distance away from the Earth. There are three ways astronomers use to determine the brightness of the star: absolute magnitude, which I've just mentioned, apparent brightness, which is a measure of the brightness of the star from the Earth, regardless of its distance away, and luminosity, which is a measure of the amount of light energy released from the star's surface every second. This question is about stars. The diagram shows the orbits of two astronomical objects around a star. Add a labelled arrow to the diagram to show the type of force from the star acting on object A. So we know its gravitational force is going to be acting towards the star. So we need to draw this and we need to label it gravitational force. What is object A? Well, it's got a circular orbit around a star, so it must be a planet. Remember that comets have a highly elliptical orbit, galaxies consist of billions of stars, and moons orbit planets. What is object B? Well, we've got a highly elliptical orbit, that means a very squashed oval shape, which means it's a comet. State the name given to a large collection of billions of stars. I keep answering these questions before I see them. It's a galaxy. Physicists classify stars according to their colour. Each group of stars of similar colour is called a spectral class. The table gives information about colour and surface temperature for three spectral classes of stars. The Sun belongs to spectral class G. Complete the table by suggesting values for the missing surface temperatures. So remember, the hottest stars are blue and white and the coolest stars are orange-red. So we need to increase 5,600. That'll give you lots of options here. Anything higher than 5,600. I'm going to go in with 8,000. And we need to go lower for spectral class M, so I'm going to go 3,000. There are stars in the universe with masses much greater than the mass of the Sun. Describe what happens to these high mass stars when they leave the main sequence stage of their evolution. So we need the high mass and we need it after the main sequence, so don't be talking about protostars. So we know that the star expands to form a red supergiant. A large explosion called a supernova occurs. A black hole or neutron star is formed. Hertzsprung-Russell diagrams. It's important that you're aware of the relevance of a Hertzsprung-Russell. So why do we bother drawing them? It's because they allow us to determine what stage of its life cycle a star is at. So is it a white dwarf? Is it a red giant? Is it in its main sequence? And you will find several options when it comes to the y and x-axis labels. So here we're looking on the y-axis at absolute magnitude. Remember, this is a measure of the star's brightness at a standard distance away from the Earth. Do make sure that you know how to label the axis in terms of the numbers. We start at 0, we go up to -5, which is actually the brightest star, and then we go down to +5, +10, +15, which is actually the dimmer star. Along the x-axis here we see colour. Remember, colour represents the surface temperature of the star, so the very hot stars will be blue, the cooler stars will be red. So do bear in mind we've got absolute magnitude and colour of star here. However, it's also possible to plot luminosity on the y-axis. So remember, that's the measure of the amount of light energy released from the star's surface every second. Again, keep an eye on these numbers on the labels. And then on the x-axis, it won't be any surprise to you know that another option is temperature, because after all, colour and temperature are very closely linked as far as stars go. Again, you'll find the hottest stars over on the left-hand side and the cooler stars on the right-hand side. So as well as being prepared to label the X and Y axis, you do need to be able to loosely plot the various stages of a life cycle. So I call this a kind of backwards slash. This is where your main sequence will be. So if you're given information about the absolute magnitude and colour of a star, and you find that it's located somewhere here, you can safely say that the star is in its main sequence, and indeed the sun would be found here. The sun is our star, and it is indeed in its main sequence. The forces are balanced and it's carrying out nuclear fusion of hydrogen. The bottom left corner, you'll find the white dwarfs. Now the white dwarfs will be very hot. Look, they're on the blue-white side of the colour spectrum, and they're also going to be very dim. So look, the small hot dim stars are down here in the bottom left-hand corner. Top right corner now, you'll find the red giants. These will be bright, as we can see here, and they'll also be cooler. To the left of the red giant and slightly up, we have the supergiants. And if I scroll down and show you the luminosity versus temperature graph, look, the shape of the graphs remain very similar. So if I were you, I would get a blank piece of paper, practice labelling the Y and X labels, as well as adding my main sequence, supergiants, red giants and white dwarfs, to my Hertzsprung-Russell diagram. One thing to note is several astronomical objects do not appear on the Hertzsprung-Russell diagram, such as the moon, and the reason for that is because the moon does not emit its own light. It's fundamentally not a star, and the surface temperature of the moon is far too low. The Hertzsprung-Russell diagram shown can be used to classify stars. 3 regions in the HR diagram are labelled P, Q and R. Let's just get that sorted. Look, here are our main sequence stars. Then we've got our red giants up here and our white dwarfs here. Do familiarise yourself with these diagrams. The boxes show the 3 regions and different astronomical objects. Draw a straight line from each region to the type of astronomical object contained in that region. So I've already done that. P I said was a white dwarf. Q I said was a main sequence. And R I said was a red giant. Define the term absolute magnitude. It's a measure of brightness of a star at a fixed or standard distance away. Cosmology. How did the universe come into being? Now, the theory which is most widely accepted is known as the Big Bang theory. The Big Bang states that the universe is expanding after exploding suddenly in a Big Bang from a very small point, and in the Big Bang, space, time and matter were created. Now, obviously this all happened billions of years ago, so what is the evidence which supports the Big Bang? Well, broadly speaking, it can be divided into CMBR, cosmic microwave background radiation, and redshift. Now, CMBR, cosmic microwave background radiation, appears to be the same in all directions throughout space. And what this implies is that all parts of the universe were in contact at some point in the past. Then there was a huge explosion which sent the CMBR into space, evenly distributing it. Now, if you look at the wavelength of CMBR, you find that it has increased over time, and so that suggests that the universe has cooled significantly since the Big Bang. So if we were to summarise the evolution of the universe from the Big Bang to present day, we would say that the universe started as a single dense point, and since the Big Bang, the universe has expanded and the universe has cooled. Now, the second piece of evidence supporting the Big Bang theory is the redshift of galaxies. But what do we mean by that? Well, light from distant galaxies appears redder to us, and if we contemplate the electromagnetic spectrum, specifically the visible light part, remember that the colour red has the longest wavelength, and then violet, so a bluey purple shade, has a much shorter wavelength. So the fact that that light appears redder indicates that the wavelength of the light has increased. And what could be the explanation for that? It's the fact that the galaxies are moving away from us. And actually, the greater the redshift, the faster the galaxy is moving away. And so if we were to go back in time, that light would appear less redshifted, the galaxies would be much closer to us, and actually we think that they were all in a single dense point, bringing us back to our origin of the universe. One equation which people don't like, but I don't want you to fear it, is the one which links wavelength, galaxy velocity and speed of light. You will be provided with this equation, which states that the change in wavelength divided by the reference wavelength equals the velocity of the galaxy divided by the speed of light. The speed of light will always be a set value, 3 times 10 to the 8, in a similar way to the specific heat capacity of water, which is 4.2. So if we go through this example, a distant galaxy contains hydrogen, which emits light of wavelength 610 nanometers, the same as hydrogen on Earth. So I'm hoping it's clear to you that that is our reference wavelength. The wavelength of the light from the distant galaxy is measured at 685 nanometers on Earth. So the distant galaxy is the galaxy that we are comparing it to. So if we actually do 685 minus 610 to get 75 nanometers, hopefully you can see that that is our change in wavelength. So we're being asked to calculate the speed of the distant galaxy. It's up to you how you want to write this out. So delta means change in, lambda means wavelength, lambda 0 means reference wavelength, but you might not like that. It does look a bit gross. So it's absolutely fine to write out that equation how you see fit. Then just sub in all your values. So our change in wavelength is 75. Our reference wavelength, remember I said, was 610. We're after the speed of the distant galaxy. The speed of light, we were told, is 3 times 10 to the 8. So do 75 divided by 610 and then multiply that by 3 times 10 to the 8 to get the speed of the distant galaxy as being 3.7 times 10 to the 7 meters per second. Give 2 pieces of evidence for the Big Bang theory. First one is CMBR, cosmic microwave background radiation. And the second piece of evidence is redshift of galaxies. Explain how this evidence supports the Big Bang theory. So we're going to start by saying that CMBR appears to be the same in all directions, implying all parts of the universe were in contact a long time ago. I'm now going to talk about the redshift of galaxies. The furthest away galaxies are travelling the fastest away and show the greatest amount of redshift. Astronomers have used supernovas in distant galaxies to investigate the expansion of the universe. Light emitted from a supernova at a wavelength of this was detected at Earth with a wavelength of this. Calculate the speed at which the galaxy containing the supernova was moving away from the Earth, and here's your speed of light. So write out your equation. Change in wavelength over reference wavelength equals speed of galaxy divided by speed of light. So the reference wavelength will always be what the Earth can determine. So it's actually going to be this one. It says that the light was detected at Earth with a wavelength of 7.7 times 10 to the minus 7. So that's actually your reference wavelength. Your change in wavelength is the difference between these two numbers. Write them really carefully. You're after the speed of the galaxy, and the speed of light remains at 3 times 10 to the 8. Sort out the left-hand side by doing 6 times 10 to the minus 10 divided by 7.78 times 10 to the minus 7. It's fine to break this down into lots of steps if you're more comfortable doing that. And then multiply 7.71 times 10 to the minus 4 by 3 times 10 to the 8. To get 2.31 times 10 to the 5 to 3 significant figures.